Okay. Welcome to this year's OCaml workshop. We have an exciting program ahead of us. But first, let me bore you a little bit with a few opening words. We are very happy to have received that many good and cool submissions. So thanks to anyone that submitted. We tried to get in talks within a diverse range of topics. And I'm sure there are ways in which it could be even better, but we are quite satisfied with the result. When I say we, more specifically, Sonia, Heinz, and myself were responsible for organizing the workshop this year. I'm here now. Sonia couldn't be here in person because right now she's 8 months pregnant. But she's attending from online, and so hi, Sonia. And we organize everything together. Maybe it's even more accurate to say that she organized a lot and that I help. Right, and I should also thank all the members of the PC who actually did all the reviewing for the submissions. So that was great. And finally, thanks to the OCaml Foundation that provided funding, a little bit of funding for registration fees for speakers that needed it. Maybe one day we can dream that this would be free, but alas, that's what we have right now. And so thanks also to the sponsor for the foundation that give it money to do that kind of cool stuff. All right, let's get to the cool OCaml stuff. And for that, Samuel has been waiting. I'll now give the mic to Stefan to introduce Samuel, and we can get started.
Great, thank you, and everybody welcome to the first session of the workshop on compiler features and optimizations. Our first talk will be Samuel Vivian talking about the design and implementation of modular explicits.
So hi, so I'm going to present you the design and implementation of modular explicits. So this is a new feature that PR was created to the compiler a few months ago, and it's currently going under review. Hopefully we'll have it inside the upstream compiler in the next year. So it's joint work with Didier Rémy, but also the implementation was done with the help of Léo, Guillaume, Pierre, Nathanael, and Vincent from the Flamta team at OCaml Pro and Léo at Jane Street. So a bit of history. In OCaml, since 3.12, we have a feature called first-class modules that enables us to store a module inside a value, or first-class value, such as the sum all m above. And we can also unpack those first-class modules inside to have, once again, a module which enables us to use it as a regular module to take out fields inside this module. An example of the use case of this feature is to have dynamic modules inside our code, such as having a module that is defined depending on a flag. So depending on the value of a flag, you take module M1 or M2, which can be useful in some cases. So just say, oh, depending on how big I'm going to run my code on, I will use one implementation or the other of a certain library. A general use case of module is that first-class module is doing a let module to unpack the module locally, and this creates a scope. This happens a lot when you're having a function that take a module, first-class module as argument, and you might not be used to the syntax, but rather the one with syntactic sugar, where you unpack directly the first-class module as argument. However, there is some limitation with this syntax. So first example, I have a small signature add, which defines type T and addition on this type. And I want to write the function double that takes an X as argument, a module of a signature add, and use this module to do the addition between X and X. And we have a small error message when trying to type this code saying that X is of type alpha and was expected of type m.t. So this is a bit strange, but the second line says us that, oh, it was a problem with scope. And the thing is, when someone sees this code, you might want to write it, but you have no way of writing the type of this code currently in the OCaml compiler. And this is why the code is rejected. You cannot write the type, so it cannot be typed. A workaround will be to remove a dependency between the type of x, and the module by defining a new type, type A, and saying that the type defined inside the module M is type A, and also that the type of x is also A. In this case, you remove a dependency, and you're able to type this function. However, what happens when I want to do it with a parameterized type, such as list? I'm trying to do the same thing with, I'm defining the type with a parameterized type, but the syntax doesn't allow this. And when I'm trying to restrain the signature of set to a parameterized type, it's also not allowed. So I cannot do this. So I'm stuck. However, we can just do a first-class functor to do this. So you write a functor, store it in first-class module, and you can do this once again. However, this is hardly readable and also extremely painful to write. A small example, if I have a signature S, which defines a type T, which is parameterized, and a function singleton that take value and create a set of this type. So I want to write a function f that takes an element, a module x, and returns the singleton built from EL. However, so normally there was scholars saying this were in red, but this cannot be written. And if you want to write this code, you need to do this big code that is a bit difficult to understand. And if you manage to understand this just by seeing it, I'll be impressed. So to solve this problem, we just introduce a new type, which is module-dependent function. So this is not the same arrow as the one we have currently in OCaml because it's a dependent arrow, however, it's the same syntax, which the big thing with this module-dependent function is that x can occur inside tau. And with this, we can express all the types of the function that were presented before and that could not be typed. However, we have a few restrictions with this new type in order to be able to do things with it. First thing is that a parameter can be depended on only if it's a direct unpacking of a module. For example, if we unpack a module inside a pair, it cannot be dependent on this module. If we don't unpack the module, we cannot be dependent on the module, with just the last case where it's directly unpacking the module, where we can have a module-dependent function. And also, when doing an application, we need to directly pack the module at the application. So in a way, we're just directly giving a module and taking the module directly back in order to be able to do things. And if we stay too long as a first-class module, we're just stuck. So small example of use case, I have a module type show, which is the same thing as the type class show in Haskell. So we have a type T and the show function that converts our type T to a string. And I have two modules, that is show int and show list, that define a show for the corresponding types. And I can just write a small function show that take a model x and a value of the corresponding type defined in x and just convert it to a string. And I'm now able to write the type of this function. And from this, I'm able to print a list of integers just by giving the good module to the show function. So in a way, this is a way to emulate type classes in OCaml, just with writing the application by hand. So you want to understand how this works. So we are going to do a bit of typing. So when we have a module-dependent function, we give it an argument that is of a good type. We just take the return type of the function, and we replace all occurrences of a bound variable by the module. However, this does not respect typing in OCaml currently, because in a module path and a type, we can just have a module name and projection of a path to a certain field. We cannot just write an arbitrary signature or an arbitrary module inside a type. So to be able to do this, we need to be able to extract the module M to a path, and this path can be written inside types. But this is quite a huge restriction, meaning that when doing an application of a module-dependent function, you cannot just write a struct. However, just by doing a small eta expansion, we create a temporary path that can be used. And the OCaml compiler is able to do this through typing by just imagining that there is an X doing this and inlining replacing all occurrences of a bound variable by this x, and then eliminating the x from the scope and replacing it with all type dependencies that use this x by the definition of a corresponding type. And in a case of generative module, when you create a new type that is locally defined, then you have a scope escape. So we don't have any problem with soundness. And lastly, all this feature is also working with so the thing that we want in OCaml to be able to have principal types, which means that we, in some cases, want to be able to type without caring about the ordering of typing, and this feature also handle the principal mode because we want to have this kind of soundness in some cases, such as when typing standard library. So if I go back to my example, some of you might have noticed that the syntax that I used to define the show function is the same one as the one we currently use with first-class module. So you might want to ask, but this might cause a problem because we're already able to type some example of code with another type. And if we have two different types, this might pose a problem. However, we define both types to be compatible. In the cases where x doesn't appear in the return type, we have a module-dependent function that is not exactly dependable. So in these cases, we define both to be equivalent, and typing just go from one to the other, depending on which one is more expressive for the use case we're going to do. And also, unification does a few things that might be considered black magic, such as when doing unification, we merge both types together in order to propagate information. However, when unifying two module-dependent functions, we look at them up to alpha equivalence, meaning that we might be able to switch between x1 and x2, which might pose problem when looking at tau1 and tau2. In order to solve this problem, we unify both names together, meaning that after unifying those two module-dependent functions, we only keep one name out of both. So if you have an example using Modular explicit in the future, and you see that your function doesn't have the same bound name that the one you use at the beginning, it's just that during unification, we've merged it with another name that was written somewhere else in your code, and we need to choose one out of both. So this might seem a bit strange in types that are shown or in error messages, but it's perfectly normal. But as we are doing unifications on name, we can do capture with it. So meaning that when unifying both names, if x1 was already appearing in tau2, we're just binding the variable somewhere else, and this might be a bit problematic. So we've added a small check to ensure that we're not doing any capturing. This is something that already exists with polymorphic values inside objects or records. It might be a bit problematic in some edge cases with recursive types. And in this case, we might lose a bit of expressivity. However, this problem already exists with polymorphic values. And I didn't manage until now to generate an example that was limited by this restriction. So most likely, you will never see the difference, that there's this small restriction hiding somewhere in the code. And hopefully, in the future, it will be removed. So yeah, we have a cool feature that enables us to use module a bit more easily. However, there is still work that needs to be done in order to let people use module freely in OCaml inside the core language. And I hope that all this feature will one day be in the compiler. First thing will be parametric signature. So as you might have seen in the example before, when doing the restriction of a signature to a certain type, we have quite a lengthy syntax, just as when I want to restrict the signature egg to a type a.t, I need to write egg with type t equals a.t, which is quite long. And when you have lots of signatures that are going to be restricted, we might want to have a more shorter syntax to be able to write it, and a.t egg could be a way to do this. It's the same thing as parameterized type, but with a signature. Another feature that will be in the same direction will be to be able to give directly types as argument to functors. So there's some libraries nowadays that give types in a functor, but you always need to wrap it inside a module. An example of this is OCaml graph, that sometimes have functors that don't do any restriction of the type they need. And so this is quite lengthy to be always say, oh, I'm defining a module that contains one field that is a type, and could be useful to just give a type directly. And by using value restriction, we can just also give a different semantic to this kind of functors compared to regular functors that take a module as argument. And last feature that could be useful in the future will be modular implicit. So for those of you that haven't heard about this feature, it was initially proposed by Leo Watt, Frederick Boer, and Jeremy Yallop 10 years ago in a paper called Modular Implicit. And so the idea is, if I take my example with show from before, I can just define modules that I label as implicit. And afterward, when defining the show function, I can just say that the module as argument will be an implicit argument with a syntax that looks a bit like implicit argument in rock. And then when doing application, I can just omit the argument because we know which module will be given based on the signature that is already restrictive and the fact that we know that the argument is a list of integers, so we only have one module that can be given as argument. However, in some cases, you might have another module that you might want to give, not be restricted with, like with type classes in Haskell, of the fact that you have a type class, so you cannot define a new one for the same type. In those cases, you can just give it by hand and give another module by hand that is not the default one. It's an implicit argument. You can use the default one or give your own. So as a conclusion, modular implicit is a new feature that does not increase expressiveness, but greatly increase conciseness. And also this feature escaped the original goal that was just being a step towards modular implicit, and now it's a cool feature that just can be used as a feature itself. However, it's still just a step toward making OCaml a bit more user-friendly in some cases. And also, just as a reference from a talk from last year from Leo, we can have parametric values, polymorphic values easily with first-class module, with modular explicit, such as in this case, we can define a type T that take module as argument that just define a type, and then we have a polymorphic values. And this is a way to do polymorphic values that are given as argument to a function without having to go through objects or records or whatever you might want to do in order to have a polymorphic values that is not instantiated when given as a parameter of a function. And if you want to have a more in-depth read about this topic, there is the PR on the OCaml compiler. You can also test this branch of the compiler by using the small Opam command that are listed above. And if you want to read even more about this topic, there is a long paper that we've written with a few other people that talks about typing and soundness of this feature. And thank you. Do you have any questions?
We've time for some questions.
Thanks for the talk and for the work in implementing this. So you started off saying that we don't have a syntax for sort of introducing a locally abstract parameterized type. Mm-hmm. Would it be possible to add that syntax? I mean, I think this is useful for other things, but, mm-hmm. but in terms of sort of motivation, it just seemed, I mean, when you presented that, I was just wondering, you know, if we just added the syntax for locally abstract parameterized types, that would be another route to sort of a similar goal. What are your thoughts about that?
I think adding a new syntax type for parameterized type might be a bit complicated, because after all, we need to do unification on higher order types. With parameterized type doing unification, it's easier when you have inference, constraint-based inference. So in a way, I don't think it's that easy to do it in the OCaml compiler as it is. However, one thing that we most likely will need in the future is to be able to restrict signatures to a parameterized type, such as when having a function that take two modules as argument, and we want to say that both modules define the same parameterized type. This is something we cannot do currently. But having a type A with a parameterized type, I think this might be a bit complicated. But hopefully someone will find a way, I hope.
Okay, thanks.
No?
Thanks for the talk. So in OCaml, you also have applicative functors that creates a new kinds of module paths, so-called application path. Do you also support application path in modular explicits?
Yeah, with modular explicit, which is just a way when doing application to be able to do the types correctly, as it's not doing currently with first class module. However, we support all the features of typing outside with types that currently exist, which is the case for applicative functors.
Awesome, thanks.
Any further questions? Actually, I have a quick. Do you want to go again? I have a quick question. Have you thought about what should happen with subtyping coercions if you feed a dependent module or module-dependent function in?
Yeah, so for answering this question, we thought about it. The main thing is that when doing subtyping, we want to do subtyping without doing any code generation. So to do this, we need to not change too much the type of a function, and we want to have a function that have the same runtime value. So to do this, we need that the two modules that are given as argument needs to have the same runtime representation, which means that you cannot reorder values inside the signature, but you can reorder the position of types, and also you can remove a few types that are unneeded from the signature, or add, depending on how you see the subtyping.
Cool, thank you. Did you have a... yeah.
So this introduces dependency between function arguments. So that sort of implies that function arguments need to go in a certain order. How does that interact with labeled arguments that maybe you sort of partially apply a function with labeled arguments such that then we need to eta expand and sort of get things out of order? Does that pose a problem?
Currently how labeled arguments work is that when doing the typing, we reorder the arguments in the good order. And so if you have a module-dependent function, it will try to look for the module that is given as argument. And if this module is given, you can just type the function with this argument and continue typing the rest of the function afterward. But this creates a barrier that we type directly this argument compared to other labeled argument currently where you type the arguments after distributing and unpacking the type of the function. And when the type of the module is not given and we cannot remove the dependency, in this case, we just failed saying, okay, you cannot remove the dependency.
Okay, thanks.
Okay, let's thank the speaker again.
This was working before.
Hey.
What? Okay, that's fine.
Nice. Okay, our next talk will be on the F-lambda2 validator by Irene Yoon.
Okay, cool, thanks. Today I'll talk about our work on the F-lambda2 validator. I'm Irene Yoon, a postdoc at INRIA, and this is joint work with Chris at Jane Street. So a quick primer about the F-lambda optimization pass. So the F-lambda optimization pass is a pass in the middle end of the OCaml compiler, as many of you probably are already familiar. And one of its main features is for inlining function calls. So for example, if you have this simple factorial function, and if you have let n that applies 4 to the factorial, then it can inline the function call to factorial so that you can do some compile time reduction of terms so that at the end, let n can be just reduced to 4 times factorial 3 instead of having the whole body of the factorial function. So the F-lambda optimization, there was a sort of F-lambda1, the original optimization pass, and behind the scenes, it had an ANF-like representation. And it also had a lot of internal representation. So ANF is this form where you have a series of let bindings in a certain normal form. And this IR has several characteristics, such as it's not necessarily preserved under function inlining. For instance, if you were to just imagine in this small code snippet, G containing some let bindings, and if you were to inline that in the below snippet, you would see that it's no longer in normal form because you have nested let bindings, and typically you have to do this sort of joint point rewriting where you have to rewrite in order for your term to be in normalization, which could be inefficient. And certain control flow optimizations are also difficult to reason about. So F-lambda2 is a ongoing development that is for better inlining for the OCaml middle end. And unlike F-lambda1, it is a sort of CPS-based transformation inspired by compiling with continuations continued, suggested by a publication by Andrew Kennedy in 2007. And in terms of the compiler, it sits in the same location as the F-lambda pass, where it takes it in lambda terms and it targets a new IR called F-lambda2, and it emits CMM terms. So in terms of the design choices that can be made at this level of the IR, it's actually not so straightforward what kind of IR you might want to have and what kind of optimization you might want to have. This is actually a research question that many people have been thinking about. Oh, the animation here is. So classically, there's about like 3 choices that you can make at this level of the compiler in terms of IR. Many known things, these are classic ideas that has been researched for decades at this point, is forms such as SSA, where each variable has only one definition site, which is good for data flow analysis used for IR such as LLVM IR. There is also commonly used continuation passing style, a variant of lambda calculus where functions do not return but apply a continuation to their result. And one nicety of continuation passing style, for instance, is full beta reduction is sound in the sense that if you see these 2 snippets, you can see that for the left-hand side expression, if you were to apply lambda x dot 0 to f of y, if f of y, if f were to be non-terminating or were to have side effects and you wanted to do full reduction here, it would be unsound because in the case that f were to indeed have some side effects, you would be throwing away that side effect. Whereas if this term were to be in CPS form, you wouldn't be throwing away the side effect. So this is one reason why you might want your IR to be in CPS style if you care about function inlining. And as I've hinted at earlier, ANF is a variant with flat let bindings, which requires commuting conversion, which can be inefficient. And in fact, there has been other works by various people that discusses the whether or not we need to choose one decision over another and the advantages and disadvantages over the other. So our contribution specifically is about F-lambda2, which makes some interesting design decisions in this domain. So our contribution is a validator for F-lambda2. So the F-lambda2 pass is under active development. Currently, it's around 95,000 lines of code. And it combines various ideas from this domain where the IR itself is a mix of CPS, ANF, and direct style. And it uses data flow analysis to do some pretty advanced optimizations in one pass where it does both CSC, it does speculative inlining, unbossing, value tracking, and match, and that's just several of the features that is covered with F-lambda2. So our goal in implementing this validator is we wanted to see whether or not it was possible to write a declarative specification for the reduction behavior of F-lambda2 to better understand what this optimization pass is doing and whether or not we can validate its outputs in a relatively simple manner. So how do we do this? So we took a pretty classic approach. We tried to do translation validation. So this is a way of checking a posteriori the correctness of a run of compilation versus compare this to compiler verification, which shows the correctness of a compilation pass. So this was also inspired by several similar approaches, such as validating register allocation and spilling by Rideau and Leroy in 2010, and semantic equivalence checking for HHVM bytecode by Nick Benton in 2018. So what we do at the high level is we do some semantic equivalence checking of F-lambda terms. So this is the F-lambda2 optimization pass. So the F-lambda2 IR has a simplification pass which goes from the IR to the IR itself, and it does several, it does a simplification step which implements several optimizations at once, which I mentioned, such as match, function inlining, and CSE. And in order to validate this, we actually define a translation to what we call an F-lambda2 core term, which is a new IR that we defined in this validator, which is a more lambda calculus-like view to the IR. And then we defined a normalization scheme for this F-lambda2 core term so that these translated terms, we can check for its alpha equivalence. So if the translated and normalized terms are alpha equivalent, we say that they're validated. If not, we don't guarantee any results about the input and outputs of the F-lambda2 optimization. So with a validate flag, given a source ML program and a single run of the optimization, we can show the semantic equivalence between the input and output using our scheme. So I want to also explain what was the kind of the core features of this F-lambda2 core terms versus F-lambda2 without going too much into detail. So F-lambda2 core, we thought about it kind of having the lambda calculus hat on and seeing F-lambda2 in a little bit more of a simpler way. One core difference between F-lambda2 core and F-lambda2, of course, is when you want to do function inlining, you typically don't want to do full sub-expression inlining because oftentimes that results in much more inefficient terms. But for the sake of validating our terms, actually being able to do having full sub-expression in argument position is okay, as long as we're okay with term explosion. So F-lambda2 core allows for full sub-expressions in argument position so that there can be more aggressive inlining in the normalization process. It's more like the lambda calculus in that there's more uniform representations of lambda terms. We have uniform closure bindings. So there are closure bindings in F-lambda2, which represents non-recursive and recursive closures. And we have unified these closure bindings so that we have a simpler normalization process. And as I've said, the translation scheme unifies all lambda-like constructs to use this same closure binding, and this makes the treatment of recursive terms a bit simpler. And Next, I'll talk also a little bit high level about what we do with normalization. So without going into too much detail, the normalization, there is kind of a tension here where we want to normalize, but we cannot fully reduce at all times because inevitably it will not terminate if we continue to try to normalize and try to inline recursive terms. We don't know whether or not that will terminate. So our approach was that we try to define as simple of an operational semantics to this data flow-based optimization as possible. And one disadvantage that we do have is that termination is not guaranteed under our normalization scheme. We have no proof of termination for our normalization. And the size of the terms, although we have tried to keep it as small as possible, they tend to be quite big because we allow for full sub-expressions and arguments. So the set of operational semantics that we've defined through experimental observations on F lambda 2, and there's rules around non-recursive, recursive, and local continuation so that we ensure certain normal forms for recursive closures so that we can still do interesting optimizations such as being able to do argument elimination in case an argument for a recursive call happens to be invariant. Another interesting thing is that we still also do, although it's not shown in the rules here, we also do in the process some very simple static analysis, which is needed for checking some recursive terms and preventing further term explosion. So in terms of results, the test suite was the OCaml standard library for F lambda 2 of the OCaml compiler. We tested it on the AMD EPIC 7002 processor with time limit of 20 minutes per file. And for the standard library, out of 67 files, we were able to validate 45 files. And 14 files we did not validate, and 8 files timeout. And the validator itself is around 7,000 lines of code, whereas the F lambda pass is 95,000 lines of code. So at the end, it is less than 10% of the size of F lambda 2. So we were happy that the validator is still relatively small relative to the pass. So modulo the limitation that will be discussed in a couple of slides. And a note about performance. The performance itself is bimodal. So out of the 59 files that do not complete and do not time out, 43 completed under a second. So this chart is saying all the files that did not time out. And then this is seconds, and then the cap is around 20 minutes. And only 5 required more than a minute in this case. And from our observation, the speed did not seem to strongly correlate with the program size, and we still need to do some further investigation on why these specific files time out. So, of course, there are still some limitations on this work. Results show partial success, but we also encountered some optimizations that are challenging to validate with this specific technique, such as cross-module inlining, which is a useful optimization, and it's not a theoretical obstacle, but for the performance of the validator, the term size would explode already. The term sizes get quite large testing without cross-module inlining. Nuanced approach would replicate F lambda 2's cross-module inlining decisions because F lambda 2 does have inlining tree that reports when it will inline or not. And another subtlety is function argument introduction and elimination. So F lambda 2 does some fancier static analysis on when a certain argument is invariant over recursive functions, and we do not have such a static analysis pass. We only have a very simple way of detecting it, so this is also for future work. And the current development is available up in the link above. Thank you.
Thanks, and we've plenty of time for questions.
The ones that didn't validate, is it you run, was it because the validator is not complete, or is it because you actually found errors in the optimizations? You had some that didn't validate, as something like 14% something.
Right. The parts that did not validate was partially because of it was the limitations that we've discussed here, because we weren't able to some of the simplification done by the F-Lambda 2 compiler for the standard library was using cross-module inlining, and it wouldn't, or function argument introduction and elimination, and it wouldn't validate because we didn't support these yet. Yes?
Hi, this is great. The F-Lambda 1 pass output a sort of script that it sort of says what it did, sort of. Does F-Lambda 2 does that? And if it did, would it help you, guide the explosion a little bit to do the validation?
Right, so I'm not too familiar with F-Lambda 1, but F-Lambda 2, perhaps you're talking about sort of the inlining decision tree.
Yeah.
Yes, F-Lambda 2 does have that as well, and if we were to use that, perhaps we'll prevent more term explosion. Yeah.
Okay.
Thank you.
Thanks for the talk. So I'm curious now, which find the timeout in the OCaml standard library? I imagine probably OCaml internal format things?
Yes. It cut off, but it's there. I think that's, yeah.
So there is one OCaml internal file that doesn't time out and the other does, something like that?
Yes, for some reason.
Oh, thanks.
Thank you.
Thanks for the talk. So you introduced a new IR because it would make your life easier to write this validator. You also think that it would have helped write F-Lambda 2 in retrospect by choosing this new IR instead of the current IR that's used?
It could have helped, but there are practical necessities that exist in F-Lambda 2 that we could safely ignore in F-Lambda 2 core. So there are several things, such as there's more identifiers in F-Lambda 2 because certain identifiers, like the memory representation, is actually important for efficiency reasons. So I think the part that could have helped is perhaps the uniform representation of closures could have helped. But otherwise, there are practical details in F-Lambda 2 itself that do need to exist there. So I think perhaps the closure representation and the identifiers, I think, could have helped in the design itself. But right, there's still a lot of complications in F-Lambda 2 IR.
Thank you.
Yeah. Mm-hmm.
Did you find incorrect optimizations when running your validator?
No, we did not find any incorrect optimizations using the validator. That's for, hopefully, if this becomes more robust, we'll find some.
Could you try it with a buggy version of the optimizer? See how good it is?
Sorry?
Could you try it with a version of the optimizer that you know has a bug and see how well this catches it?
Yes, we have not tried this. We could, yes.
Okay, let's thank the speaker again.
Thank you.
Great. And the third speaker for this session is Richard Eisenberg, who will be telling us about a non-allocating option.
Is this picking me up? Yes, good. Okay. Hi, everyone. Thanks for coming to this talk. So this is about, this talk is about, well, our old friend option. And so here we have this nice option type, which is really a wonderful thing, right? Because it means that using option, we can have better error tracking, right? If a function returns an option, we know it might fail in some way, and then it might return none. It forces us to check this result. All very nice things. Let's look at an application of it. So here we have a square root function, but of course negative numbers don't have square roots that can be represented in float. So we check if the float is less than 0, then we just want to return none. Otherwise, we want to return the actual result wrapped up in a sum. But at runtime, what this is going to do is we're going to have this box on the right that contains our actual answer. But then there's this other box in the center, right? And this represents the sum constructor. And we don't really want that box. We just sort of want to say, oh, well, it didn't fail, so here's the answer, right? And this extra box, this causes an extra allocation, and sometimes we want to eliminate that. In many applications that we have, both in Jane Street and outside of Jane Street, I'm sure, it doesn't matter if we sort of allocate a little bit extra. The function that calls safe square root is going to pretty quickly pattern match on this and eliminate it. But sometimes we have a couple of applications, at least within Jane Street, where every allocation matters. And we do want to make sure that we don't have any of them. And so this kind of paradigm or a model isn't available to us. So we're unhappy about this box. What can we do about it? So we want to avoid this allocation. So the idea behind all of this is not a new idea. Aspects of this approach will be new, but this first idea is not new. We want to store some x just like x, right? Instead of doing this extra step, let's go instead of this just to this. Okay. The immediate problem that we run into is, well, we still have to tell the difference between some and none. And so to do that, we're going to have to come up with some representation of none that's distinct from every other value that's out there, right? Because we don't know what the sum is going to wrap. So if we're going to have a none that's distinct from it, then it has to also be distinct from every other value out there. Well, here's an idea. Let's just use null. Well, what do I mean by that? So here I'm using null to represent the bit pattern that's just all zeros. In contrast, other values, we can have a pointer. Well, a pointer isn't going to be all zeros because it's going to be a pointer to some valid memory address, so that's not null. Or we might have a tagged int. But a tagged int, well, it's tagged, so the bottom bit is 1. So even the int that represents 0 still ends in a 1 bit. So it's also not null. So that means that null here really is distinct from all other values that currently exist in OCaml. We still have yet another challenge, and that is that we need to tell the difference between none and some none, right? Because I was saying earlier that sum of x is going to have the same representation as x. So that means that if none is represented by null, then some none, well, according to that logic, also has to be represented by null. And this looks like a problem. And so there's a bunch of different ideas that we could attack in this space. The particular idea that we're choosing here is to disallow alpha option option. But of course, we can't do that because option has been around for a long time. This would be backward incompatible, so we're not going to do that. Instead, we're going to create a new type we're calling or null, and we're going to disallow alpha or null or null. So actually, in the end, we're not going to, and it's going to have its own constructors, null and this. So we can return, this square root of something. So actually, as much as I've been phrasing this as an improvement on option, it's not really. We're going to keep option exactly the way that it's been. There's going to be no changes there that we're looking at. Instead, we're looking at creating a new type or null that has this, that's more efficient, but it lacks the ability to nest. So it's not strictly better or strictly worse, but it's just a little bit different, yet we're expecting it to be quite widely applicable. But I've said here that I want to disallow alpha or null. The way that I'm going to do that is by separating out with null types from no null types. So the idea here is that we're going to take all of the types that exist in the world, and well, all of them today are no null types because all of the types that exist today don't have a null in them. But this new or null type is going to be a with null type. And those of you who know about at immediate, this is kind of the way at immediate works, in that we distinguish some types as having an immediate representation. If you don't know about at immediate, that's fine. You don't need to understand this talk. But if you do know about it, we're sort of connecting into the same kind of logic here. Okay, so let me sort of demonstrate all of this a little bit in our implementation. So we can go out from here and over to Emacs, and this is showing up. Is this big enough? Can I have someone in the back nod? Yes, good. Okay, thank you. As you can see here, we have an implementation. The implementation that I have here is all of the type system features. The runtime stuff is still a little bit in progress. And I want to give credit to my colleague Diana Kalinichenko, who's done all of this implementation work. And much of the design. I sort of started it, and then she found a whole bunch of problems with it, and it's been refined a bunch. I shouldn't even say that. This was a collaborative effort among a bunch of people, and anyway, as with everything at Jane Street. So we have type T1 here, and this works just fine. Let me prove this to you. I can compile this file, and it compiles without error. So we'll see there's other examples in here, but everything that we see that's not commented actually does work. So we have string or null, and then of course we can have representatives of this type. This :T1 annotation is not necessary. I'm just doing it there for emphasis, right? It's just an ordinary. Whoops, didn't want that. It's just an ordinary type. Okay. Not only for pointery things like strings, but it also works for inty things like int. Let's see what's coming up next. Okay, so we might want to put these things in a list. Well, it turns out that the built-in list, sort of the way that it's defined out of the box, is going to accept only no null types. So I have to redefine it here to be with null types. What we're going to eventually do, we haven't done this in our implementation yet, but it actually just go in and change list to accept the with null types. So users won't have to do this. This is sort of a little fragment because we're still building this as we go. But with this redefinition, we can now say that that list can contain with null types, so string or null list works. But we don't want to be able to say string or null or null. And so indeed, if I uncomment this, whoops, that's going to fail because that's broken. Sorry, that's just like the command line was, oh, what's gone on here? Something's bad has happened. Okay, there we go. Okay, I don't know what I did wrong there, but I fixed it. So we can see this. Oops, that's not what I meant to show. There we go. So we can see here that we get an error message saying that the kind of string or null is value or null. That's one of these. That means that that string or null is a with null type, but it must be a subkind of value, and value is the no null types. This is the types of everything since the birth of OCaml. And so it's saying that there's a sort of this kind error here. And that's exactly the kind of error that we want. This string or null really should be prevented. So let me re-comment that and then continue. Okay, so now we get to see some of the challenges that arise around type inference in these things. We're going to need a little bit more space. Okay, so here I have S1. Very basic module type. And one question is, when I make an abstract type T like this, is that a with null type or is that a no null type? And this is sort of a hard decision to make from a language design point of view. We have decided to make this a no null type because we think that will turn out to be more convenient. One consequence of this is that this module M1 is going to be rejected because it instantiates T with a with null type. So indeed, if I uncomment this, and then go down here, and then hit some buttons, then I get an error. And let's see, type T equals string or null is not included in type T because they have different kinds. Okay, so that's what we would expect if plain type T is required to be a no-null type. On the flip side, we can define F1 down here, right? So here I can take the x.t and put it in an or null, right? If I made the other choice around what the meaning of abstract type T was, then F1 would fail instead of M1. And we think that in general, we're gonna have more trouble if we allow M1 and disallow F1 than the other way around, right? Because in an OCaml program, there's many, many, many abstract types, right? And we wanna just be able to put them in or null. There are not quite so many collections, as we'll see a little bit further down in the file. So let's go on to more examples here. Whoops, gone too far. So now here I have S2, which has this annotation that says that this abstract type T is a with null type. So that allows M2 now. I can say that I can have type T be instantiated with string or null because I declared that T would be a with null type. And by the way, types that don't have null, like string, we can still use them in type T. It sort of doesn't use the full space that's available, but that's fine. We don't have to use the full space that's available. But we can't do module F2, right? I said that x.t in this case is a with null type, so I can't pack that in another or null. And so again, this echoes some of the situation with at immediate, that we get certain capabilities, but then we lose other things, right? It's a trade-off. Okay, that's the end of the demo. Let me go back to slides. Okay, so one challenge here was sort of figuring all of that stuff out. There are further challenges around type inference, but there's not quite enough time in this talk to go through them all. But if you ask me after the talk, I'm happy to explain it to you. So another challenge that I do want to spend a few minutes on is around flat float arrays. So the flat float array optimization in OCaml means that if we want to create an array of floats, we use a different representation than all of the other arrays out there. And so when we're allocating an array, we have to decide before allocating the array whether it's going to be a float array or not. And we have to do this in a polymorphic context, potentially. I'm thinking, for example, in the compiled version of the init function, right, which creates an alpha array, we need to do some work to figure out if alpha is a float or not before allocating the array. So the way that this happens in practice is by figuring out what is the first element of the array, looking at that, and then if it's a float, then we allocate a float array. If it's not a float, then we allocate a non-float array. For that analysis to make any sense, we need this separability property. So the separability property says that, that for a given type, every value is a float or every value is a non-float, which sounds like most types should just sort of have this property, but it turns out not every type has this property. So for example, OCaml allows unboxed existentials, and if you create an unboxed existential that just wraps up the existential variable, you'll get an error saying that this type is not separable because some values are floats and some values are not. So this is actually, every time you make a type declaration in OCaml today, this separability check happens. I should say, it's not clear, everything on this slide is in every OCaml out there. This is not specific to sort of our version or anything we're doing at Jane Street. But float or null is not separable, right? Because float or null has both floats and also null, right? So in practical terms, if we created a float or null array, we might get the first element might be an actual float. Then we'll think, oh, the whole array must be floats. And then when we try to put a null in, well, there's sort of no room for that in the bits, right? All zeros is a valid float. It's just not a valid value in OCaml because floats are boxed and sort of referred to by indirection. So this float or null is not separable. So we have a problem. And it means that we just can't have a float or null array, right? That would be really bad. Well, we have two obvious ways of stopping ourselves from having a float or null array. One is banning float or null, and the other is banning or null array. Well, if we think about this first option, if we try to ban float or null, the way to do that is we could just sort of gratuitously label float as a with null type, and then that would successfully ban float or null. But that's also going to mean that if we have an abstract collection type, an abstract parameterized type T, it would ban float T. And we think that's going to be pretty painful. So we're not going to do that. Instead, we're right now choosing to ban alpha or null array. And if you want to pack a bunch of or nulls in an array, we can do that with a uniform array or some other collection, right? There's other ways forward, but to use the built-in array that has this flat float array optimization, we're just not going to be able to use it with floats. With or null. So there's actually an alternative solution to this that was floated, I think, 3 decades ago, about just sort of counting the number of sums that precede a none. I could talk more about this. I think this was maybe originally mentioned in a paper by Jacques, but maybe it was coming from somewhere else. But we found a reference from '95 that sort of mentions this alternative idea. But this would mean that the option type is not separable, and that would just be a huge backward compatibility problem. So we can't do that either. So again, I'm happy to sort of tell more details about that. But there might be a way forward. If we didn't have the float array optimization, there might be another route that doesn't involve sort of bifurcating the space of types. Implementation, as you can see, is mostly complete. So we're steaming ahead with this. And sort of once it settles, we'll be looking forward to upstreaming this feature. And that's all I've got. Thanks very much. Happy to take questions.
We've some time for questions.
Okay. Jagari. First, a remark. So this idea, actually, we tried, I discussed that with Xavier a long time ago. And I think Xavier even implemented it. It was a slightly different version when you use the fact that no value in the heap has a type that is 2 modulo 4, a value that is 2 modulo 4, so that actually you can have a whole bunch of, so you can represent knowns of none, etc. But actually, this seems this didn't work very well, so we just dropped that approach.
What didn't work very well about it? I mean, so it's incompatible with this float array optimization, but otherwise, that seems good.
I suppose it was not that efficient.
Really? That's surprising.
That means, well, then you have some work when you access. So you have to shift because it can be. So you have more tests to do. I don't know. You have to ask Xavier if he remembers. My other question is that a natural candidate for or null is optional arguments, but then that means that you cannot use or nulls as functional arguments. Your thoughts on that?
So that's a good point. I mean, it would be nice to use this for optional arguments. Right now, it seems with the current design that we won't be able to do that because it wouldn't be backward compatible. Because you can have an optional argument that is itself an option. So I guess we could have that be an option, but pack into an or null. It's when we've thought about it, the type inference challenges make us think that we're not going to go in that direction. We might hopefully revisit that, but right now there's not a concrete plan to use this for optional arguments as much as we want to. Yes.
So when talking about performance, you said, well, there's these cases where you have to do where you can't allocate it all and it's useful there. And maybe in other contexts, the allocations are short-lived enough. But I actually just don't believe this story because I think there are lots of contexts where you have long-lived data structures, large data structures that have lots of optionality baked in them. You have some big record with lots of optional fields. Go model a Google protobuf or something. And then we also have internal stuff that looks like this, where there's just a lot of RAM that is dedicated to these extra indirections. And I wonder to what, if we've thought at all about the question of if you took this kind of stuff and applied it to some of the kind of standard things that this community has worked on, like cook or something like that, whether getting rid of pretty thoroughly getting rid of the non-related indirections would have a performance effect on that kind of code as well.
I mean, I imagine it would. The example at the beginning of the talk would most likely be one of these very short-lived nodes. But of course, we store options in records and in other structures, exactly as you say. Removing them would likely increase performance. I don't have data to present at this point about that, but absolutely. I mean, we expect once this is available to sort of make a little campaign of trying to change over options into or nulls, and we'll test to see the performance changes there.
All right, thanks for the talk. If you have an or null under an ADT or something that goes under a layer of indirection, is it then safe to call that not null because you won't immediately have this null problem, or do you go all the way down to check for nulls?
I'm not sure I understand the example. Just explain that again.
So if you had something like, I'm not sure exactly how pairs are implemented, but if you had int or null star int or null, would it be safe to call that type not null?
Yes.
Okay.
Because I mean, as long as like what you just described would be a sort of a boxed pair.
Right.
So that's represented by a pointer, which itself can't be null, even though the components can be null. We're in sort of another branch of work, right? We're looking into unboxed types, and we can have an unboxed tuple, and then there's a little bit more complication around how this propagates through unboxed types that we're still trying to work out.
All right. Yeah. Thanks.
Sure.
And let's thank the speaker again. And our final talk from this session will be Nick Roberts telling us about mix blocks for storing more fields flat.
Hi, thanks for coming to my talk. My name is Nick Roberts. I work on the OCaml compiler at Jane Street. Everything I talk about in this talk, a version of it is available in our branch. So I will be talking. I will be talking about an extension to OCaml's runtime representation of values that gives the programmer more control over memory layout and therefore more control over performance. The name for this extension is mix blocks, and the basic idea, I'll give it away at the beginning, is that the heap objects tell the garbage collector which fields it should scan. Not exactly revolutionary, but there's some ideas here that I think will be interesting, or may be interesting to the OCaml community. And there's certainly more to explain there, and I'll get there shortly, but let me start by saying a few words of context. Mixed blocks fit into Jane Street's work on unboxed types, which is kind of like a kinding system for OCaml that lets the user avoid automatic boxing of numeric data, among other things. Mixed blocks, the topic of this talk, relate to unboxed types, but I'm not going to be talking about unboxed types in this talk. I'm only going to be talking about the parts of mixed blocks that are a small diff, both like conceptually and in the actual implementation, against the OCaml that users are already familiar with. Okay, so let's begin. How does memory layout affect performance? Well, I mean, it does, but many ways, the focus of this talk will be on indirection, kind of similar to Ron's question, actually, at the end of Richard's talk. Right, so and by indirection, I mean layers of pointers that code needs to follow in order to access the data of your data structures. And more layers of pointers means more work is expended, both by user code in order to compute with the data, but also by the garbage collector in order to traverse the heap and accurately track liveness of values. Right. Before I get into the rest of this talk, I'm going to walk through a quick example of the runtime representation of an OCaml value. I think many people are familiar with this already, but I think it'll still be useful to walk through. Right, so this record R here is a record of 3 fields, 2 of which are 64-bit integers in 64. And here's a schematic of like how this is actually laid out at runtime. There's a lot of detail in this diagram, and most of it's actually irrelevant, but I will draw your attention to the large number of boxes and the large number of arrows. There are lots of pointers in this representation. There's a lot of indirection. Each int64 value actually ends up being represented as a pointer to a 3-word heap object that consists of a header followed by like some generic operations, followed by the actual 64-bit payload of the object. And then R, the 3-field record, is this 4-word heap object with pointers to the int64 objects. This ends up being 10 words. That's kind of, it seems gratuitous. The thing I'll be talking about here, just to preview what mixed blocks look like. Yes, to preview the mixed block representation, you could imagine laying out the object something more like this, where the raw numeric payload is stored directly in the object. And this would take less memory to lay out. And just some terminology that I'll introduce. I will say that the I1 and I2 fields here, I'll get to the syntax later. I'll say that they are stored flat in the object. That just means that the numeric payload is stored directly rather than being a pointer to a heap object. And I will also call this a mixed block because it mixes pointers, like the pointer to the string s, with these fields that are stored flat. And the exact challenge of this I will get to shortly. Actually, immediately. The challenge with storing a field flat is the garbage collector must be told about it. In particular, it must be told not to dereference it and treat it as a pointer. So let's look at OCaml's prior art to understand this challenge more. It's already the case that OCaml stores some numeric fields flat. If you write a record that has, that all of its fields are floats, that ends up, the float values are stored flat in the heap object. And the way that this is okay from the garbage collector's perspective is the tag in the header word of the object conveys that the object is a flat float record, and thus the garbage collector should not look at the fields. The fields, you know, they might actually just look like a null pointer, for example, and you know that's one kind of pointer that the garbage collector should certainly not dereference. Yes, but this prior art is not enough for our purposes, or is not enough to kind of encode all the shapes of heap objects that you might want. The kind of current situation is that the garbage collector interprets a tag to mean either that it should look at all of the fields of a heap object, or it should look at none of the fields. This is all that is available in the current interpretation, with like a finite number of, like a very small number of exceptions. Yes, and what you might reasonably want is such an object as this, where the first field must be scanned. It is a pointer to a string. We must know whether or not that string remains live or not. And it might be important to the user's use case that the remainder of the fields are stored flat so that they require less indirection to access. That is, you might want some mixing, hence mixed blocks. Okay, so I'm going to talk about our design. As I alluded to at the beginning, it's not like especially revolutionary, but there's still some ideas that might be interesting, and this might be something that people might be interested for their own applications. Yes, so the design that we have implemented is one where unscanned fields can't appear, where unscanned fields can't appear prior to fields that the garbage collector must scan. So raw numeric fields can only be stored in the suffix of the heap object. And to implement this, we use the header word to encode the length of the prefix of the heap block that should be scanned by the garbage collector. This new data in the header word is effectively an encoding of this variant here, where the first constructor uniform is the old kind of backward compatible meaning, and the mixed constructor is the new thing. Happens to be in our design, and this may preview how many bits we have stolen to make this work. Only up to 255 scanned words before, in order for something to be allowed to be encoded in this way. Yes. So I guess the draw of this approach is it allows us to support mixed blocks without needing more space. Like, we don't actually need to make any heap object take up more space in order to support this encoding. Certainly, some questions arise. I guess one question is, do we even have enough room in the header to accomplish this? On 64-bit systems, the answer is like clearly yes. So let me tell you a bit about how this works. So what we end up doing is we steal a byte from the header word in order to encode this length. The current kind of layout of the header word on existing OCaml is the bottom byte is used to encode the tag. This is the byte that that conveys the information I said before of whether or not the garbage collector should scan the fields. It's also what's used to distinguish between the constructors of a variant. The next 2 bits are some garbage collector metadata. That's not actually relevant to this presentation beyond the fact that we are deprived of these 2 bits. Finally, the remainder of the header word is used for the size and words of the object. So if we steal 1 byte from that, we reduce the kind of expressible size of OCaml values from 4 petabytes to 512 terabytes. With either of these, the runtime system would have quite a bit of trouble even initializing the value in the first place, so this is clearly just fine. Yes. So the thing that we will use this byte that we've stolen for is to encode the length of the scan prefix +1. The only reason we do the +1 is so that we can use 0 as a sentinel value, meaning that the block is uniform, this backwards compatible meaning where either all fields are scanned or not. Yes. Okay, so there's, just to walk through a quick example, here is the example from before. The thing that we encode as the scan prefix length +1 is 2, because there's one field that is scanned. And on like kind of the old style of object, its header actually ends up looking exactly the same as before because the top byte remains 0. This sentinel value meaning uniform. Yes, so certainly there are some things to talk about with this design. One advantage is that the scanned fields remain immediately after the header. The scanned fields are the ones that the garbage collector is going to have to dereference and traverse anyway. So it's convenient for the reading of the header, which the garbage collector does, to also load the scanned fields in the same cache line as the header. It would be silly to put the unscanned fields there because then they would be loaded for no reason whatsoever. Yes, so this is friendlier to hardware caches. Another kind of nice thing is that we've made the scanned prefix length logically separate from the tag. Pattern matching code that just cares about what constructor of a variant that it's looking at merely needs to look at the tag. It doesn't also need to care about the scanned prefix length. Further, we can allow any constructor of a variant to be encoded as a mixed block. That doesn't affect pattern matching. Yes, and there's an obvious limitation, which is like, I claimed that these were called mixed blocks, but certainly it seems to be a very limited class of mixing, where it's all like scanned things followed by unscanned things. You can't have an object where, say, the first and fourth field are scanned, and the remainder of them are not scanned. Yes, and this is different than the approach that Haskell takes, where it actually allows for like kind of richer kinds of mixing, but this comes at the expense of requiring kind of more space in the representation of the value to encode which fields are scanned and are not. Like, I think for some values, Haskell, for example, just has like a bitmap of like which, like a raised bit indicates which fields the header should scan, and this kind of takes more memory. The advantage of our scheme is that we haven't actually increased the size of an OCaml object in order to do our encoding. Yes, and then another limitation, which might be a bigger limitation for some use cases than others, is that we don't support generic comparison over an object that has these unscanned fields. You can come talk to me afterward if you want like a detailed example of why this is difficult, but just for like kind of a flavor of it, imagine that your field encodes like two 32-bit floats. There you might want the like 0 and -0 to compare as equal, even though they're in like separate halves of the word. Don't worry if that was confusing. I said it very quickly. But in any case, the takeaway is that comparison is difficult to, maybe just impossible to implement. This happens to be okay for the style of programming used at Jane Street, where we avoid generic comparison in favor of PPX-derived comparison functions, but it might be more of a limitation for other use cases. Yes, let me talk about the syntax a little bit. Right, so like we've defined a new type, a new shape of object. How do users get the new representation? One option would just be to silently give it to people. Like if you use int64 as a field of an object, maybe now suddenly the field starts being stored flat in the object. We've decided not to do this and instead opted for a style where the user explicitly requests this shape of object. There's a couple reasons for this. One of them might be, well, users may have written external C code that is tied to the actual runtime representation of values. Also, if fields continue to be boxed on projection from the record, it's not always going to be an optimization to remove this boxing. It should really be a user choice. And then also, I don't know, it's nice to be explicit about what memory representation you're actually getting and the performance characteristics that you want. And aside, this isn't actually the syntax we've used at Jane Street. There's like, the syntax that we used fits more into like the whole system of unboxed types, so doesn't really fit in this presentation, let alone on this slide. Yes. And we don't currently, like it is currently the case in our implementation that the order that you declare the fields matches the order in the runtime representation. This means that we have to statically reject some ordering of fields, but this isn't like inherent. You could imagine, having the compiler actually pick the order of the fields that that allows the value to be representable. Yes, I've done kind of a silly micro benchmark, but just to drive home the fact that indirection is slower. What I've done in this benchmark is I've varied the number of fields of type B that are marked as unboxed, and just run a benchmark where in a loop I've summed up like all of the fields of such objects. You might be surprised that this runs faster because I just said that fields are boxed on projection. The reason why this doesn't end up affecting this benchmark is that because I'm immediately computing with the thing I've projected, a compiler optimization can remove the need for the box and just add the raw bits of the float of here the int64 into the accumulator. So yes, indirection is slower. Another application that is maybe interesting is there's actually another kind of like subset of values in OCaml. I've already talked about ones that need to be scanned and ones that need to not be scanned, but there's also ones that need not be scanned, like that are fine to look at, but that you don't have to. And for those, again, this syntax doesn't actually exist, but you could imagine like being able to mark those, and which would tell the garbage collector that it doesn't actually need to traverse those fields. The reason you might not want to do this is if you care about generic comparison. So it's, again, it's not something that you should blindly do. Yes, and in fact, if the garbage collector doesn't look at a field, it is faster for it to do its work. Not surprising, but it is nice to see a kind of a line that goes all the way to 0. Yes. Yeah, and there's some related work that you might be interested in. That's all I have. Thank you for your attention.
We have some time for questions.
Thanks. What kind of types can you flatten? So you showed us in 64. I guess an array wouldn't be able to be flattened, but in the middle, what can you do?
Yes, so the types that we support flattening right now are kind of the numeric types. So int64, int32, float, native int, I think. Yes, those are all the ones that come to mind. I think it could probably be extended to more kinds of types, but those were the ones that we focused on for this. Yeah.
Thanks.
Nice work. I wonder if you've done some sort of real-world comparisons on the GC scanning performance and how often you can use this encoding to sort of speed up the GC.
Yes. So yes, I didn't mention this, but users have actually started using this feature in production. I think the performance we haven't seen any case where like someone has come back to us and said, oh yeah, like my program's running 5% faster or anything like that. I think for what we've seen so far, people have reported like more modest speedups, like 1 or 2%. But I think for like a hot loop of code that you're really trying to optimize, this kind of technique is invaluable. Yeah.
Thank you.
Thanks.
So this is very nice for integers that are boxed and we can represent them unboxed. Another place where I usually find is lots of indirections in programs is when you have nested records. Do you imagine it would be possible to sort of inline or fully flatten records with some annotations, especially if you add the reordering?
Sure. I think such a thing could probably be implemented even in the absence of the things that I talk about in this talk. If you're just thinking about like kind of like inlining the fields of one type definition into another type definition. But yes, I think in conjunction with the ideas here could allow for like this idea to carry,
Yeah, you
carry
probably
through
need
that
the
idea.
reordering as
Yes.
well to make it.
Yes, yeah, with the yes, for something like that where you inline one record into another, yes, like the reordering becomes more essential. Also, if you wanted to represent modules using this same thing, because they're, well, this is too complicated of an example, but like modules are another case where kind of the reordering is essential to make it usable for users. Yeah.
Thank you.
Thanks.
Okay, let's thank the speaker again.
All right, hi everyone, and welcome to this second session on developer experience. So we will start with Florian, who's going to talk to us about better error messages.
So yes, so let's start this session about developer experience by going at the lowest level. By going at the lowest level, at the compiler level. So I will present my work on trying to improve the cooperation between the OCaml compiler and the other tool in the ecosystem. So like many parts of my work, everything starts with a simple mistake. So for instance, adding a non-necessary argument to a functor application, which gives you a quite long and quite colorful error message. But it's quite probable that for many of you, you are more used to this version, which is a little less colorful. But strange, what happened to the color? Well, the problem is that from the compiler developer point of view, the error message is this nice algebraic data type. But when we go to the plain text output, and we lost a good part of this information, and sometimes tools resort to things like that to try to understand if what we are saying is an error or a warning. So it's a OCaml lecture that tries to match if the content on SCD would start with error or with warning. So there's kind of an impedance match here. So we have on one side nice structured information, on the other side we have ad hoc lexing. Fortunately, there is a well-known solution to this conundrum, which is to have machine-readable output with like JSON, S expression. This is implemented by many compilers like GHC, GCC, Clang, Rust, and more. And it's a nice way to decouple the content of the compiler diagnostic from its presentation. So like this, editor controls the best way to present the information present in the editor or other tools. So maybe it's time to end this talk. I mean, I just have to admit this, and everyone will be happy with this very nice readable XML. XML. Oh, do you mean that you didn't want XML? But maybe JSON. But I have heard that OCaml people quite like X expression. So maybe this one. And then there's something strange here. Do you see this last field, a footnote? A footnote in an OCaml error message. Does anyone have seen anything like that? Probably not, because it's a new feature, a new field in OCaml 5.3, which is not out, so probably no one has seen it. Which means that part of the problem is that we have an evolving compiler diagnostic, and if we want to improve the cooperation between the compiler and the tool, we need both to have a nice way to have an explicit versioning policing, so tool can consume the compiler output, and also a format-independent way to describe algebraic data type. Because, well, I'm an ML compiler writer. I don't want to write this on serializer. I would much rather describe what my IDT my algebraic data type are doing. So let's talk about subtyping and versioning policy. So the first very easy bit of versioning is just to add the error field. So like this, if a tool reads the fact that the metadata is as version 1, they can know that they are saying a compiler diagnostic that they understand fully. So which is nice, which means that I can write a tool that reads the version 1.0 of the compiler diagnostic, but then what about version 1.2 or version 2.0 or version 2.4.3? Well, for the last one, probably it's fine to ask the question, wait a minute, which sensor is it?
But for the second one, version 2.0, if I've written a tool a few years ago, I would really like that my tool is still working. And even more so, if the compiler developer made a minor difference, really my tool should work without me having to do any kind of work. Otherwise, you will end up in a situation where every time the compiler update its diagnostic format and content, every tool needs to be updated, which is quite heavy and painful. So what should we do? Well, this idea that a tool writing for version 1 m.x should be able to write a diagnostic for version m.x plus k simply means that this later update of the version should only refine other information to the previous compiler diagnostic. This is a classical notion of subtyping, which means that what I want is that minor update of the compiler diagnostic are subtyped or the previous version at the same major version. And it will be nice if both the compiler and the tool will be able to cross before between later version and previous version. Unless from new version, because yes, from major version at some point maybe we want to add completely new information and no one can predict the future, so breaking version is kind of unavoidable. So, but let's try to precise a bit what I mean by subtyping. So the easy case is record, because for records, the classical subtyping rules tell you that you can add a new field to a record type, promote an action field to a required file, or deprecate a field. Very easy about that. So for instance, imagine that I want to add a manual link to your report to be able to point the user to, well, this error message is explaining somewhere in the OCaml manual. But if I were to write in previous version without this field, we will be reading, for instance, the kind of the report. The fact that there's a new field somewhere doesn't matter for them. So this means that I can add this new field and consumer writing in the previous version just need to ignore the field, which is easy to do. The problem is with variant, because the job of creating the new field for the variant constructor is to delete a constructor. Because, yes, if I have a sum type with some constructor, and I say that, well, no, I will never emit this constructor again, the consumer just ends up with some date code, but it doesn't need to update anything, which works, but it means that every time I have a variant, I would be stuck with never adding any kind of constructor. And, well, I like my sum type and algebraic data type, and I will need to evolve them at some point. So we'll need some more specific, let's say, more exotic subtyping rule for constructors. So first, easy rule to implement is to allow minor update to expand the argument type of a variant constructor. The third rule is to introduce a new derived variant constructor. So what does it mean? So let's go back to the example for deleting a constructor. I just remove a constructor, it's fine. What do I mean by expanding a constructor argument? So for instance, previously in my report kind, I have a report warning and a report warning as error. And then I have, and then if you look at the content of the argument of report warning was a concatenation of the warning number and the warning name. At some point, I would like to be able to split the two, to avoid the tool trying to parse this string to recognize the warning number and the warning name. So, and a nice way to do it is to decide, well, I would just expand the content of the argument of report warning from a string to a record that contains this special field content that would hold the previous content of the constructor, and then the new fields. And whenever a tool that was expecting to see a string, see a record, it knows that, well, I just have to look at the content field and my string will be here.
So this works. But then it means that you can only provide more information under a variant. I can still not add a variant. So what can I do to add a variant? So the idea is that maybe I can try to find a compromise and say that my new variant constructor is not completely new. And it is, in fact, kind of similar to a previous existing constructor. For instance, I could add an int at a kind of error and say that if you don't know what is an int, it's probably a little bit like a warning. It's not an exact mapping in terms of semantics, but for tools that only know about warning, it's better to have the information that there is a strange warning going around rather than just fail completely and pretend that nothing happened. So here, in terms of representation, this means that we first have the new constructor and an approximative field that say, well, if you didn't understand what was that constructor, you can try to read that as a report warning. And with this, we can at least add some constructor if we can approximate their semantic to previously existing constructor. So better than nothing, and there's many cases where, yes, int is a bit of a warning of alert. But let's try to speak a bit about the version 2.0. So when, at some point, you really need to delete fields that have not been used for 10 years or 20 years, or maybe at some point you really need to add constructors that have a completely different semantic than previously existing constructor. And then this means that you would need to have a major version update and say, well, I'm doing a breaking change, and I cannot avoid that without being able to predict all the features. But even in this case, there's still things that you want to do to preserve backward compatibility. In particular, you want to keep a set of deleted variant, constructor, and type to be certain that you are never able to delete a field named A, and then a few versions later, recreate a field A with a completely different semantic, because then people that would miss the delete could be very confused by the completely new semantics, and it's quite cheap to do. Okay, so we have a versioning policy. How do you implement that? So the main idea is to start from the algebraic data type and consider that I have algebraic data type with version information. So for instance, with the information that this field has been created at version 1.0, this field has been created at version 1.0, then expanded, and I think and similarly for report. So this is a notion that is finer than what exists in OCaml. So what we can do is we can implement an embedded domain-specific language for describing version additive in compiler libs. With that, it's quite easy to log the additive that you are describing. And also, you can implement externally serializer, schema generator, versioning policy, validators, and things like that. So how do you do that? So algebraic data type is the mixture of two features, type expression and nominal type. So for type expression, because we are only exposing data and quite simple data, you can use a standard JDT encoding that describes the type, that describes your type expression. So here we have a string argument, an int argument. We can combine then with list. There is this constructor that says that if you have a description of a sum of a record, I can create a field or a constructor with this content. And for the nominal side, well, you need to have fresh name for nominal type, and fresh name when you are embedded inside the language means fresh type. And fresh type, you can use a generative functor. So here it's a functor for creating a new record. So here it's mostly a history of version, some metadata information like the name of the new record, the generative argument, and then you have a new identity type, and some way to create new field, deprecate a field, delete it, make it required. So typically, if I want to describe the error kind of previously, I can create my new record and describe the fact that yes, I have a kind fields which contain a value of type kind, which will have been described previously, and I can describe my field like this. Then I can have a log type that mostly is taking some information, a printer, some setting for the printer, a version, a record type, a way to print on files or STD out and generate a log where I can log field by field partially to simply implement the serialization to the low-level device. And implementing a format implementation is just the classic printer for JGT. You match over the type description. You have some primitive for exposing all the fields defined in a record definition or destructuring a sum type. And it works. So typically, let me see if I can find, yeah. You can have a OCaml top level. Yes, that tells you that when you do 1 plus u, the output at the top level is the description that you have computed free. You have the metadata feed that is telling you that is the version 1, and it is fully valid. And you can also have warning if, for instance, if you never remember if it is running with a S or without a S. So this is a yeah, so it is without a S, and then you have a top-level error that tells you that the warning was an unknown directive, and you know about that the information came from the top level, and it is a top-level error rather than the compiler error inside the top level. And like I say, you can also implement JSON schema. Let's say that describing algebraic data type in a format that is not really aware of some type can be quite long. So this is the schema for the compiler diagnostic in full. But it's possible to do that. So this work, there is an upcoming PR for this work. Like I say, you can implement external tool for exporting JSON schema and validating the additive history or adding a new serializer. It's easy enough to add serializer that I could implement a toy XML validator between 2 sessions in ICFP, which is nice. And if you have feedback, they are more than welcome.
We have time for some questions. Okay, I can ask a quick question. So you're planning to do the translation from, transforming the schema from one version to the other version. Don't that put a lot of burden on, well, you, the compiler developer, to handle all this annoyance, which we sort of had to deal with, parse AST.
Yeah, so it's part of the problem that someone needs to deal with the annoyance, and the compiler is kind of a centralized place. And let's say that the compiler diagnostics doesn't change that much, so I don't expect to have that many change, and it could be automated quite easily. If starting early, you could have a generator that starts from the additive description and output everything. It's most of the case. But yes, so in fact, it would be quite nice to lift a lot of this declaration, this description at a meta level. But meta programming in the OCaml compiler is quite heavy. So I wanted to start with embedded DSL and then possibly later generate things.
Okay. Okay, then maybe no. Go
on. So thanks. That looks cool. From what I remember from a few years back, a number of the errors at the output of the compiler were at the time fairly like in a string format, like already processed. Like a type error would just be, okay, actually you just got this error message and the structure has been lost. I guess this is somewhat orthogonal to your work, right?
Yeah, so it's still connected because one of our reasons to move to structured diagnostic is because, well, I would like, in fact, to have even more structure in the compiler side for error message, but already existing structure is already hard to process by tools, so it doesn't make sense to add structure when nobody would ever use it. But this means that once we have the structure, it would be easier to motivate people, or to probably to motivate me to have more semantic error messages to expose really the error and not the processed strings. So some of the things that is not exactly shown here is that, in fact, the error message is already not outputted as a string, but rather that the format string that contains formatting information. So tool can see which tag were used and can re-implement them. And then they can redo the formatting to adapt the geometry, to not have an error message that was formatted for 80 column wide terminal when you are in VS Code.
Yeah, that makes a lot of sense. Yeah, thanks.
So I was expecting to see just a great story for OCaml errors, and if I understand correctly, the story is much bigger, right? So it's common to see cases where you can define data structures and automatically derive serialization. But I haven't seen all the versioning logic being built in for you. So isn't this just a much bigger idea than what you're building it up to be?
Well, theoretically, it could be used by anyone. I'm cheating a little bit because for the OCaml compiler, I only need the serializer, not the deserializer. So it removes a little bit of complexity. But yes, otherwise, it's quite generic way to try to describe your algebraic data type in a versioned way. With some limitation, because yes, the type expression doesn't cover the full power of the OCaml type system, because once you try to explain GIDT inside GIDT, you are hurting yourself quite a bit. So, but most of the time for compiler diagnostic, you want to have pretty simple data type that can be pretty well, that can be printed. So,
thank you. All right, let's thank the speaker. And next, Ulysse will present the ongoing quest to improve the tooling available in editors, and in particular for occurrences and refactoring.
Okay. So I'm going to talk about a very exciting new feature for OCaml tooling. which is not only coming soon, but is already available. So this is project-wide occurrences. And it's still a progress report because there are a lot of improvements to do from where we are now. So first, I just want to remind you what are the tools that are involved in OCaml toolings. And it starts very low. It starts with the OCaml compiler and build systems, whose mission is to, of course, drive the build of the necessary artifact and provide enough information for downstream tools to actually give you interesting facts about your code. And most of the time, complex features require modification at that level. Then there are the language servers. So most of the intelligence is coded into Merlin, which also vendor a modified typer from the compiler so that it can do more things and get more information without having to modify always the upstream compiler, but it's not always possible to not do it. And OCaml LSP, it's actually just a front end for Merlin, so the intelligence, the analysis functions are the same as Merlin, but it speaks an alternative protocol, which is the standard LSP protocol. And then you have editors, plugins, that is a part that you are interacting with directly in your editor. You have a plugin for Emacs and Vim that speaks the standard ad hoc Merlin protocol, and LSP-based plugins for all editors, but only VS Code right now has OCaml-specific LSP plugin. And it works quite well, and it has given us typing information, smart completion, jump to definition, occurrences in the current buffer for a while now, and we probably had that even before a lot of other languages. But project-wide occurrences required a longer time to come. And it's because it's a quite hard feature to add to retrofit to OCaml. And it required a lot of changes to the compiler, which started a lot of years ago with having a work to correctly identify precise definition in the compiler with unique identifiers. And more recently, a robust way to actually know what is the definition of that thing in my code, which is a complex problem in OCaml because of the complexity of and the flexibility of the module system. But now we have these tools, so we can continue building on them. So first, I just want to give some definitions. So when I'm speaking about occurrences, I mean every appearance of an identifier that is related to the same thing. So here in this example, we have 3 occurrences of the identifier x, one in the declaration of the value named x, one in the definition of this value, and one is in the usage of this value, m.x. So there is 3 occurrences of the identifier, but only one usage of the value named x. And so the talk is about towards progress-wide occurrences, because what we have right now is not project-wide occurrences, it's project-wide usages. So what we provide is a way, given any values path, to highlight all the other usages of the same value in the entire code base, in the entire project. So the basic idea is very simple. We are going to iterate on every location in the type tree. Look for the definition of every value path we find. This gives us a UID, the identifier to that definition. Then we want to group all the location of the usages that share the same UID inside an index that is written to the disk. And this index can be queried by tools to actually give you the answer you want. But of course, it's not so simple. So I will come back a bit with how to find the definition, because it's one of the mainly interesting part of this design, but it's not new work. So we proposed that in 2022 with Thomas Refis and Leo White. So I will not enter into any details, but if you are interested, there is a talk and paper for the ML workshop 2022. So finding the definition of something in OCaml is hard. For example, here, if you want to know where X comes from, so before shapes, the tools were trying to walk the type tree up and decide, oh, is that the definition of X? Is it not? Do I need to walk further up, etc.? And basically, there is a need for the tool to understand the module system, which is the role of the compiler and not the tools. So what we propose with shapes is a way to do it in another way. The compiler will build information that record what functors were applied at what moment, so that we can keep track of definitions during typing, so that tools can use that to recover the definitions. And so shapes are terms of simple lambda calculus with projections, and identifying the definition of value, it's the problem of that is reduced to reducing the shape of the path in that calculus. So I will give you a very fast example, but I won't enter into details because there are already information about it. But let's say we want to identify the definition of X from the functor application of F to M. And F is simply the identity functor for simplicity. So first we need to build the shape that corresponds to this path. So here it's a projection to access the X field in a structure. And the structure is the result of the application of the functor F. So it's an application of the shape of F and to the shape of M. And the shape of F, it's an abstraction of a variable, which is a functor argument. And the body here is just the argument itself because it's the identity functor. So if we beta reduce the application, we get the shape of M because it's the identity functor. And then we simply need to look at, okay, but what is the shape of M? And it's a structure with, you have information about all the elements in the module M. And we simply need to project from it to get to a leaf, which hopefully contains the UID of X. And all these shapes that I made appear magically are computed by the compiler and can be reused for computation by the tools. So our initial idea was to do it as a pass after compilation from the CMT files, because there is a type tree in the CMT files, iterate on the type tree, and reduce every shape. But in fact, it's not possible, because reducing shapes from anywhere, from any value path in the module might require internal shapes that are used by the compiler to compute the final external shape that is written in the CMT files, but is not accessible anymore from what is written in the CMT files. And written these shapes in the CMT files is very space expensive. So what we decided to do is to do a partial step of indexation in the compiler itself. And so we iterate on the type tree. We reduce partially the shape. We don't want to perform full reduction because this might require loading shapes from other compilation units, so it would break the separate compilation scheme, so we cannot do that. But we reduce them partially, so at least there is only requirement for external shapes to finish the reduction, not internal things that might have disappeared. We write that into the CMT files, and then we have an external tool that will finish the reduction, aggregate usages, and write the index to the disk. So let's take a very simple example of the building scheme for the indexes. So here we have two libraries with source files. And what I'm going to describe is what we've implemented in the Dune rules that are available today. So first, the OCaml compiler will build the CMT files. There is a new flag to use for the indexation to happen. Then we use a new external tool, which name is OCaml index, and it will take the CMT files you give it, finish the reduction of every partial shapes it might encounter, and write the final index, which is just a map from UID to list of locations. And then the build system is also responsible to write the Merlin configuration that will list all the indexes that need to be taken into account to answer queries for this project. All this can be done by building this new index, new alias, which is OCaml index. So then, when you query for a value, you have the cursor on the value path in your code, and you query for occurrences. Merlin or LSP, Merlin via LSP, will first identify what is under the cursor, build the shape that corresponds to that path, reduce it, it obtains a UID, then it can load external indexes to get all the corresponding usage of the same UID in the project, and it will also index the current buffer in real time to get the latest version of it, because we cannot rely on file system artifact for the current buffer. And it will return all these locations. So this is available right now with all the latest version of everything, so you need OCaml 5.2 to use it. And I will try to do a demo that will obviously work. So I have here I have only release version of tools. It's not a preview or anything. It's really what you can get if you have everything at a good value. Is the size large enough? So first, I'm going to start from 0. So it's Merlin code base, and then I will build the index, and I can build it in watch mode, and it will build anything that I need to work on my code. And each time I modify a source file, it will rebuild the index. So you're sure that the index is up to date when you query for occurrences. The warnings are from Merlin custom parser, which are not related to this. So now that it's built, I can open a source file. It's really, I don't have mirroring. Oh, it's here. And I can look for things. So let's, for example, locate from string. So it's not, it's an example with not a lot of occurrences, but you see that I not only have result in the current buffer, but in the entire Merlin project. So maybe something that is more pervasive. So logger dot. Okay, here I have all the calls to the logger. So there is a bit more across the code base, and I can navigate to them, of course, etc., etc. It also works for types, for constructors, and for modules. But for modules, it will only show you the direct usages of modules. So modules that appear in path so far are not supported because there is not enough locations stored in the long ident in the compiler for us to do it in a sane way. So yeah, here are all the usage of hashtable.create. So I guess that's useful to know. In fact, it's a really, it's really enjoyable to navigate your code base using this tool. So it's a great way to rediscover things. Here, just another example is a Dune code base. And for example, it can be very useful to know what are all the rules that are added to the context. So you can grep for them and get all the results. So yes, and yes, I wanted just a last one, but I don't see very well. But just it also works with very fastly with things that have a lot of occurrences. It's really efficient and useful. So I really encourage you to try it and report, of course, any issue you might encounter. So what we have right now, it's already a very powerful navigation tool. We have project-wide usages. It's a great way to analyze your code base, to look for specific things, or just enjoy jumping around aimlessly into your tree. It also works, as I said, for modules, but only direct usages, types, constructor, and labels. And we are already working on multiple improvements. So there are some issues with interface files because the UID in the compiler were not actually unique. Inside the compilation unit, there was the same for interfaces and implementation, so it makes it hard to guess who is who. But this is already merged and will be ready for 5.3. Also, here the build system, the OCaml index alias, it will build everything in your project, but maybe that's not always what you want. So we want to provide more fine-grained way to have occurrences in part of your project. And we are still missing a lot of information for project-wide renaming, which is the next big step for this project. For example, in this example, we have a module type and 2 modules that implement this signature. If you ask for the usage of m.x, you will only get usages of m.x, because the definition of m.x is the one in the module, the implementation of the module m. But if you want to rename the identifier x, it's not enough to rename these occurrences, because you also want to rename the declaration in the module type, and then you want to rename all the other definitions that share the same declaration, and then you want to rename all the usages of all these definitions that share the same declaration. So for that, again, we need more information for the compiler. The compiler knows everything during module inclusion checks. So there is a PR open that might land soon or later, the sooner the better. That will allow us to keep that information, which is known at the time of checking inclusion between modules, so that tools can use it, and it will also improve a lot the story with jumping from MLE to ML and other things like that. So it's really useful information to have, and it should allow us to get quite thorough renaming. And yes, try it. And report issues.
Hi, so I'm wondering how this works when you might have an identifier that you define within a module, and then that module gets packed into a first-class module, and then you try to unpack that, and then you might use that value later. How do you handle that case?
As soon as first-class modules are considered, it's a runtime thing, so we don't have any static information. So we don't progress-wide occurrences won't work with things coming from these modules.
Okay, thanks.
I've got a question about the interaction with functors, such as if you're looking for all the occurrences of ent.cmp, so for comparing function on integers, will occurrences of map.makeInt will be tagged or not, because you're using the comparison function in this functor application?
So you mean you're looking for the occurrences of CMP?
Yeah, the occurrences of comparison function on integers. Like when you do map.make, you use the comparison function when building the structure.
Yeah, it depends what is in the structure of the functor. Is the comparison function rebinded at some point or not? If it's not, I guess it should also return the other usages of the CMP function. But if it's rebinded at some point, it's a new definition, so it will stop there.
Thank you.
Hey, thank you for the talk. I'm wondering if you could say anything about what overhead the maintenance of this index adds to the build, both in terms of like build time and disk space pressure.
So I don't have precise number for the latest version, but for code bases like Merlin or Dune, which are 100K lines, for me it adds it adds a bit of overhead, but I'm still able to run it in watch mode, edit my code, and iterate as fast as before without real issues. So some issue might appear, and we want to optimize that. So there is a lot of opportunities for optimization. It's really, we did the simple thing that works right now. But if you have a very, very large library with a lot of modules, all the CMT of modules are indexed in a single step. So that plays badly with parallel thing. So we hope to optimize that, and I think it's one of the last very expensive thing we do. And querying is very fast. So far, I've never had a long query.
Okay, thank you.
Hi, thank.
You have the next speaker. Well, you. Go on.
Hi, thanks for the talk. I have a technical question about the renaming. So it seems that you need probably more information to avoid accidental unintended shadowing. So I wonder how you did that.
So that's not decided yet. We discussed it a bit with a few people. At some point, we thought that maybe listening for warnings of unused values could help us, but then you can also bypass that. So it will be a tricky issue. But anyway, I think we will need to load every source file and to type it to get syntactic things right, like puning or things like that, if you want not to break the syntax. So we will probably try to add some checks for shadowing, but we don't have a definitive plan for that yet. And it's probable that in the first version, the feature will be use it at your own risk. It's a great tool for refactoring, but maybe we can warn about places that are suspicious so that you can check them later. There is no definitive answer for that.
Thank you.
Okay. Maybe the next speaker can answer. Do you have further question? Okay, I have a question. Wait. Okay, the next talk will be about testing your modules in a better way.
Great, thank you. Hi, I'm Ernest. I'm a first-year PhD student at Cornell, and today I'm excited to talk to you today about Mica, which is a PPX extension that automates differential testing for OCaml's module system. This is joint work with Harry Goldstein and Benjamin Pierce at UPenn, supported by the National Science Foundation. Let's talk about modules. The ML module system allows for representation independence. This means I can have two modules, M1, M2, that both implement the same signature S. But M1 and M2 might implement S completely differently under the hood. Crucially, if I am a client of a module that implements S, I don't know whether that module's implementation comes from M1 or M2. All I know is that that module implements the interface described by S. Now, this is all very abstract, so let's look at a concrete example. Let's say we have a module signature S for finite sets. I have an abstract type, alpha t, and some functions for building and inspecting sets. There are several ways in which one can implement this signature. One way is to use lists, setting alpha t equal to alpha list, and making sure that my lists don't contain duplicates. I can also implement sets using binary search trees. I'm going to set alpha t equal to a tree data type, and here I have to make sure my implementation follows the canonical BST invariance. This raises a question from the perspective of a client of my set interface. Are my two implementations equivalent? Morally, does my union operation on lists behave equivalently to my union operation on BSTs? Specifically, the notion of equivalence we care about is observational equivalence, which informally says, given equivalent inputs, do the two modules give us equivalent outputs? But how do we check observational equivalence? Well, one way is to use property-based testing. This is a testing paradigm where instead of writing unit tests, we instead write properties, executable specifications that describe the desired behavior of our program. We then write generators, functions that produce random inputs of the desired type and shape. And then we check, do these random inputs satisfy our property? If yes, then we can conclude with high confidence that our implementation follows our spec. Property-based testing was popularized by Haskell's Quick Check library, but similar tools exist in many languages, including OCaml. So why should we care about this? I argue there are two reasons. The first reason is that trying to test observational equivalence directly using existing property-based testing tools requires a lot of significant programmer effort. But don't take my word for it. In a recent ICFP paper, my co-authors talked to 30 OCaml developers at Jane Street about how they use property-based testing. And the Jane Street developers said that although property-based testing frameworks are a natural use case for differential testing, they said that having to write all the property-based testing boilerplate was tedious, overwhelming, and it posed a great cognitive overhead to them. In fact, in their ICFP paper, my co-authors argue that in languages like OCaml that have rich module structures, there should be automation surrounding differential testing of a pair of modules that implement the same signature. This is the very problem we set out to solve with Mica. The second reason why I argue you should care about this is that a lot of real-world OCaml code is written using multiple modules that implement the same signature. For example, the Mirage OS operating system, as you can tell from this figure from a Mirage OS paper. So that's all the motivation. This is the interesting bit. Now, what if I told you you can take two modules, M1, M2, that implement the same signature, and automatically get property-based testing code that tests them for observational equivalence. This is exactly what Mica does. Mica is implemented as a PPX compiler extension. What you do as the user is you take some module signature definition, underneath it you write this deriving Mica directive, then at compile time, Mica automatically generates specialized quick check code using Jane Street's quick check library that tests the two modules for observational equivalence. Mica also gives you for free a test harness, which you as the user can instantiate with the two implementations that you care about. Specifically, at a very high level, what Mica does is Mica will generate expressions that represent operations exposed by the interface and tests that the two modules are equivalent with respect to that interface. So for example, if my two modules are my list and BST implementations of sets that we've seen, then Mica will randomly generate expressions that represent series of invocations to the functions exposed in the signature. Now, this is all a bit abstract at first, I understand. I'm going to talk about how this works in greater detail in the next few minutes. So what exactly is in the code that Mica derives? Well, Mica derives the following. Mica derives a few auxiliary data types, which I'll explain in a minute. Mica gives you a quick check generator of random values. Mica also gives you an interpreter, which interprets expressions over a concrete module. And finally, Mica gives you a test harness for testing the two modules. I'll talk about how these bits fit together in greater detail right now. The first thing that Mica gives you is a data type expr representing symbolic expressions. The idea is that we are going to model operations exposed in the module signature using an inductively defined algebraic data type. So what Mica does is Mica walks over the module signature, and for every declaration it sees, Mica creates a constructor for this algebraic data type, where this constructor shares the same name, the same arity, and the same argument types. So you'll notice that the empty variable on the left corresponds to the empty nullary constructor. The isEmpty unary function in the signature corresponds to the isEmpty unary constructor on the right-hand side, and so on. At this point, Mica also performs monomorphization. So it replaces all variables alpha with int, following a well-known heuristic in the property-based testing community. Now, these symbolic expressions are typed. So Mica also produces an auxiliary data type called ty, representing the types that you might see in the module signature. This is just a simple enum. Mica also defines an auxiliary data type called value, which represents the subset of symbolic expressions that are values. Next, Mica automatically derives an interpretation functor, which takes as its argument a module that implements the signature that we care about. You can think of this interpretation functor as a big step interpreter. It takes some expr, some symbolic expression, and steps it until we get a value, interpreting it over the concrete module in the process of doing so. Next, Mica gives us a quick check generator called genexpr. GenExpr generates random symbolic expressions of well-typed expressions. Crucially, GenExpr is parameterized by Thai, which is the type of symbolic expression that we expect. And GenExpr Thai promises to only give us well-typed symbolic expressions of type Thai. This is an example of a well-typed symbolic expression because we can take the union of two sets. That's good. This, however, is not good. This is ill-typed because isEmpty expects a set as its argument, but size gives us an int. This is a representation of an ill-typed symbolic expression, and GenExpr says, I will never give you such an expression. That's forbidden. Finally, Mica gives us a test harness functor, which is parameterized by the two modules that implements the common signature S. And you, as the user, can run functions in the body of this functor to test the two modules. Crucially, this functor only checks for observational equivalence at concrete types, such as int or string. We don't check for observational equivalence at abstract types, for example, alpha t. The reason for this is abstract types have an abstract notion of equality, which is different from OCaml's standard polymorphic equality. Take, for example, my set abstract type set.t. Set.t can be represented using lists and binary search trees. And it doesn't make sense to compare a list and a binary tree directly for equality, because that violates the representation barrier. Instead, this is why we only check for observational equivalence at concrete types only, because int looks the same in both M1 and M2. So how does all this fit together? Well, first, we're going to invoke our quick check generator to get some random symbolic expression. We're going to then feed that symbolic expression to our interpreter, which interprets it over a concrete module. Our test harness then repeats this process over the two modules implementing the common signature and then checks them for observational equivalence. So this is how the code derived by Mica works. Now I'm going to talk about some case studies where we use Mica to successfully catch bugs. Here are a bunch of data structures where we've tested Mica with. For each of these case studies, we've picked two modules that implement the same signature in completely different ways. Some of the more interesting examples include the regular expression matcher, where we use Mica to test a derivative-based implementation of regular expression matching versus one which uses finite automata to match regular expressions. The unsigned integers example is also interesting because we check that two libraries for unsigned integer arithmetic handle things like overflow equivalently. Specifically, across all of these case studies, Mica was able to catch 35 bugs that we inserted manually across these modules. And the bottom set of case studies is taken from 6 real-world OCaml libraries that we found on Opam. Besides all of this, we have also replicated an existing case study from the property-based testing literature. How to specify it is an introduction to Haskell Quick Check written by John Hughes, one of the inventors of the original Haskell Quick Check. This paper uses as its running example binary search trees. In particular, the Haskell artifact for this paper contains 9 implementations of binary search trees, 1 of which is correct and 8 of which are buggy. These bugs are all different, and the bugs range from the subtle to the blatant. What we did was we manually ported this artifact from Haskell to OCaml as 9 separate modules, 1 correct module and 8 buggy modules, and then we checked, could we use Mica to compare the correct module against the buggy module and see if Mica could catch the bug? And it turns out Mica can catch the bug. Each of these bugs was caught within, on average, 170 randomly generated symbolic expressions. So this is great. We can tell that Mica can be used to catch bugs. Now, at this point, you might be thinking, oh, but you only have 8 bugs here. That's not a lot. Can you use Mica to catch even more bugs? To answer this question, we turned our attention to Penn's undergraduate Intro OCaml class, which 400 students take every semester. This is a natural source of bugs because undergrads are learning and writing OCaml for the first time. As homework, students were asked to implement sets 2 times, one using lists and one using binary search trees. And then we checked, could we use Mica to test where the students' implementations were observationally equivalent? I want to make it clear that we looked at historical data from a past semester. We did not change the design of the course for us to perform this experiment. And it turns out that Mica was able to catch bugs in 107 student submissions. That's nearly 30% of the class. Crucially, 91% of the bugs that Mica found were caught within 300 randomly generated symbolic expressions. What's even more interesting is that as homework, the students were asked to manually handwrite unit tests, and the students' implementation passed their own unit tests, but Mica reviewed an observational equivalence bug in their implementation. This suggests that an automated approach for finding observational equivalence bugs, such as Mica, can help facilitate more robust and comprehensive differential testing compared to just manually writing unit tests. So that's all the case studies we've tested Mica with. In addition, we have also taken some first steps to integrate Mica with Taiki, which is a VS Code extension that my co-authors have been working on for visualizing property-based testing effectiveness. My co-authors will be presenting Taiki at WIST next month. At a very high level, what Taiki does is Taiki will visualize Mica's test results, showing you how many observational equivalence tests passed and failed. Taiki will also illustrate the distribution of the random symbolic expressions, as well as timing information regarding the tests. Now on to future work. As future work, we'd like Mica to be able to support higher order functions if they're exposed in the module signature, such as map and fold and whatnot. We'd also like Mica to support imperative code. As functional programmers, we all know that whenever we introduce mutable states into a program, we open a can of worms. And this is still something we're actively still trying to figure out. One idea we have is to add an extra constructor called seek to our symbolic expression data type, where seek of E1 and E2 represents the sequencing of E1 and E2, where E1 is an operation that returns unit. So we can sequence it using semicolon. But this is just like some initial thoughts. We have some other thoughts on how to support imperative code, but this is all future work. Additionally, we'd also like to support differential testing of functors. What does it even mean for 2 functors to be observationally equivalent? This is still something I haven't figured out, so we'd love to tackle this problem in the future. Next, we'd also like to use coverage-guided fuzzing to guide Mica's quick check generator, so that newly generated symbolic expressions tend to exercise previously untested code. There's a lot of work in the OCaml and Coq ecosystems that combine property-based testing and coverage-guided fuzzing to achieve this. And we'd like to borrow some ideas from them in the future. So to summarize, if you remember nothing else from this talk, remember this. Mica is a PPX extension that automatically derives property-based testing code for testing module observational equivalence. Today, I've shown you the design of our PPX extension. I've talked about some case studies where we use Mica to catch bugs. And I've also previewed the beginnings of a VS Code extension. That's all from me. Thank you very much.
Thank you. That was excellent. I didn't expect to see my unpublished paper to pop up there, but I expect we will have lots of questions.
Thanks for your talk. I'm very excited to use your library, but a lot of our modules don't bottom out in things that aren't abstract. What would you recommend we do? And have you considered going and looking for whether the things that are referenced in the leaves derive a quality or something, like something you can pull in order to compare?
Oh, yes, good question. By not bottoming out at something abstract, do you mean there are multiple mutually dependent abstract types that are defined across multiple signatures?
Yeah, exactly. Like in my signature, when you do the thing where you sub an int for TK. What if we don't have anything like that? Like we have a subtyping lattice module that we want to re-implement, and type is defined somewhere else.
Oh, okay, great question. I have some slides in the appendix that might address this.
You ready?
Okay, firstly, if we have like some opaque type T, then we expect the user to provide a quick check generator called quick check generator T. In the code that Micah derives, we will then call Jane Street's PPX quick check macro to desugar that. So this will allow us to generate random values of types that Micah doesn't know about. But you are right in that Micah currently offers limited support if you have multiple recursive types, multiple abstract types that are dependent on each other and defined across several signatures. At the moment, Micah is just a research tool, so we haven't run into that situation in the examples we've seen so far. Talk to me if you'd like to contribute to Micah and make Micah the best differential testing tool for OCaml modules.
Thank you.
Thanks, a really nice talk. I was wondering, what does it look like when Micah finds a bug, and have you put any work into like minimizing those or producing the smallest representation of the bug?
That's a good question. What Micah presents when it finds a bug is it will give us an S expression of the expression that evaluates the different values when it finds the bug. You can see some examples of the S expression there at the bottom of the screen. Right now, we haven't really thought much about shrinking. We thought that's more of an engineering challenge, but we ought to think about shrinking if we want to make this a usable tool. Specifically, the challenge is to shrink in a type-preserving manner. If some expression has type tau, we want the shrunken expression to also have type tau. And because right now our symbolic expressions are extrinsically typed, we haven't really figured out a way to perform the shrinking in a type-preserving manner. But that's future work.
Okay, thanks.
Hi, I'm surprised to see that the expr and types aren't parameterized by what they represent.
Very good question. I have a slide that addresses this in the FAQ. So it is possible to represent values and exprs as parameterized GADTs, and indeed one can write an interpreter for these GADT representations of expr and value using like locally abstract types and all that. But I argue this is non-trivial and hard to get right on the first time. When I first tried to write a quick check generator for this, I ran into a lot of bugs because quick check, or rather the type checker couldn't figure out how to unify different inhabitants of my GADT. And so I argue that trying to represent this using GADTs is possible and very hard. And Micah needs to do this automatically on the fly for any signature that it might see. This is why we settled for an extrinsically typed representation of symbolic expressions using regular algebraic data types.
Cool, thank you.
All right, thank you. I'm sorry we don't have time for more questions. Thank you again. And the final presentation of this session will be about the difficult task, but promising, on getting OCaml to finally work correctly on Windows.
All right. Yeah. Cool. So good afternoon, everyone. I'm here to talk about our ongoing work on building a roadmap for OCaml on Windows. We have dubbed this project First Class Windows. So one might ask why? Why should we do this? So I'm going to talk a little bit about our motivations. So let's look at some numbers first. You can see in the graph, so this is a graph of operating systems on PC usage on operating systems. And as you can see, over 65% of PCs run Windows, number one. And surprisingly, it is true for developers as well. So this is from the latest 2024 Stack Overflow survey. And as you can see, almost 60% people use Windows as their primary operating system. And this is a multiple option question. So if you can see a little bit further down, there are also people who use Windows subsystem for Linux as their primary operating system. So which puts us in a place where more than 60% users here as well are on Windows. And a bigger surprise is that a lot of OCaml enthusiasts also use Windows. I might be reading a bit much into this, but this is the stats from the OCaml.org plausible site, which shows us that 30% almost of users who visit OCaml.org are on Windows machines. Right? So here are some numbers. Let me talk a little bit about an anecdotal example that we went through as well. So last year, around the same time, at an open source conference in India called India Force, I was running an OCaml workshop, introductory OCaml workshop, which had a lot of participants, along with Casey and a few other folks. And surprisingly, more than 50% of the participants had Windows machines at a free and open source software conference. And we really had a hard time trying to set up OCaml on their machines. And finally, we had to resort to using online compilers like Replit and whatnot. Of course, this was pre-Opam, but that was when I started thinking hard about this problem of how we can make the experience of OCaml on Windows better. Right. So what's the big deal? OCaml has been running on Windows since forever, right? I'm sure people are going to ask that question. And David has demonstrated that, I think this was during the 25 years of OCaml discussion, that the very first version of the OCaml compiler still runs on Windows with very little patching. So what's the big deal? So now that, the compiler has been running on Windows for a long time, the next step that we want to think about is how can we make writing software on Windows and for Windows easier for developers. So to that end, what we are thinking about is how to get the platform and ecosystem working well on Windows. So that's essentially it. Right? So there are many ways to get there. So right now we are at a point where we have Opam working on Windows. David and the other Opam maintainers will be talking about it later today. But we want to get to a point where the developer experience on Windows is on par with other tier 1 platforms like Linux or Mac. So there are many ways to go about it. Excuse my poorly drawn diagram. But what essentially we are trying to do here is we are trying to find that path that takes us there, right? Which is what we aim to achieve with coming up with this roadmap. So how do we go about it? There are a few things that we have done and we have been doing. We did a user survey to understand what people find challenging. We also did a survey of other languages to see what it is like on other ecosystems. We have been looking at the current state of the OCaml ecosystem on Windows. And we have also started a working group for people interested in the intersection of OCaml and Windows. I'll be talking about it further towards the end. So before we dive in, right? So we had the OCaml compiler working on Windows since forever. We have Opam working on Windows recently, after the Opam 2.2 release. But even before the Opam 2.2 release, there have been bridges that have helped us to use OCaml on Windows. So these are essentially those, right? So DiskUI DKML is an open source set of software that supports development on C and OCaml. That was the recommended way to use OCaml on Windows pre-Opam 2.2. There's also this package manager SE that a lot of recent folks use, which fully supports OCaml and which also fully supports Windows. And of course, WSL, Windows Subsystem for Linux, lets you use OCaml from a Linux distribution from within Windows. And there is a small but thriving group that uses cross-compilation as a solution for running their OCaml stuff on Windows. And of course, Docker is another way that we can use OCaml on Windows. But now we have Opam that works on Windows. So the OCaml.org website is freshly updated to recommend installing Opam on Windows. So this is all you need, right? It's just 2 lines, and you have OCaml up and running on Windows. So moving on, what we did with the user survey. So this was essentially an exercise to try and understand what challenges that users face. And the good thing was that we got responses from a good mix of experienced users as well as beginners and users from different viewpoints, basically. Some quick stats. At least 30% of developers target Windows. They may or may not develop on Windows, but they target developing their applications on Windows. And 75% of participants reported trouble with installation. This was pre-Opam 2.2, so I'm hoping a lot of this is fixed with Opam 2.2 release. And 90% of participants thought the developer experience could be improved. And also 50% of participants reported that they have had a better time using other languages on Windows when they compare it with OCaml. We'll be talking about other languages in a little bit, but some quick highlights from the survey responses is that so one of the things that was mentioned in most of the response was that there isn't a blessed path that is recommended to install OCaml on Windows. And the solution is that is now fixed with Opam 2.2. There are professors, I know some of them who are sitting in this room, who teach OCaml courses, and they have had to use workarounds for letting their students who use Windows to use OCaml. And some of those workarounds are asking them to use WSL or Docker. I mean, both come with their own caveats. I'm not going to get too much into it. But again, the bottom line is that Opam 2.2 should fix this. Another thing that was highlighted was that people who are shipping products for Windows face some challenges when they're using third-party dependencies, because it's straightforward to build something that only depends on the compiler, but not so much if you have other libraries that you want to include in your builds. Cross-compilation could be a possible solution here. All right, so moving on to survey of other languages. So this was an experiment that we did to assess what the developer experience is like on Windows. So this includes a bunch of languages: Rust, Python, C, Haskell, Go, and F#. The idea here is to spot some interesting patterns and try to reuse it, and also try to avoid things that other people had difficulties with. So that's basically it. And we wanted to focus on things we have had difficulty with OCaml on Windows when we tried to use it ourselves, which is setup time, difficulty of setting up a developer environment from scratch, and handling external dependencies. So this is how we went about it. So we first go to the website of the language and try to install it. We run a Hello World program. And then we try to install the OCaml logo from the OCaml.org website. And then once it is in the system, we try to display it using SDL2. Fairly simple experiment that we repeated on all of the languages that was mentioned before. And this was our experience. It was fairly trivial with Python and F#, and I think with F#, it's sort of expected because it's part of the .NET ecosystem. It was really straightforward with C and Rust as well. And it was a bit non-trivial with Haskell, where we had some difficulty setting up the SDL to bindings. And we failed doing this in Go. It's possibly the case that we lack the Go foo to get this up and running. But I think that's the point of this experiment. We are essentially beginners who are trying to learn a new language. What is the experience like? So this was it. Some insights. All the other languages that we tried to install were easier to install and also faster to install. We are, of course, in a better place with Opam 2.2. And I also know that we haven't spent a lot of time looking at things like benchmarks and speeds because we wanted to get it up and running first. And now that we have it up and running, that's possibly coming next. The good thing is, though, we are in a better place with respect to external depths because what we observed was it was all over the place on other languages. It was either left to the user or it was left to the package manager, like in the case of Rust or in the case of Python. Of course, there's still work to do with respect to defects on Windows and cross-compilation. So there is that. So the next thing is platform tools. How do they fare right now? We tried to basically use all the platform tools and try to also build them. The good thing is most of them are usable on Windows out of the box. Right? So the first column, Opam install works, would mean that you should be able to install it now on your Windows system and be able to use it. The thing is, though, not a lot of them have continuous integration that tests them on Windows. So the thing here might be that OCaml CI doesn't support Windows yet, but the good thing is we have set up OCaml plus GitHub Actions workflow that is fairly straightforward to set up a Windows CI for. So there's still work to do, bottom line. This is a short survey of the ecosystem. There are some packages that don't build on Windows yet. And there are two things here, right? Either the package owner or the package maintainer may choose to never support Windows, which is totally fine. And this information has to be on Opam repository somehow so that we have our expectations right. The second case is that there are possibly some failures that need to be fixed. And we were in a similar place for multicore a couple of years ago. There were lots of packages that needed patches for them to work on OCaml 5.0. And Kate did a lot of work with it, with Opam health check runs and trying to identify and fix failures and making releases, etc., etc. Similar Opam health check run for Windows could be of use. Right now, the Occurrent ecosystem that forms the core of Opam health check doesn't support Windows. So when we get there, that is a possible solution to kind of expedite this process of getting the ecosystem running on Windows. Right. Yeah, so unavailable libraries is essentially what we talked about earlier. So it would be nice to have Opam repository indicate that a package is available or not available on Windows. And coming to the case of missing bindings, yeah, bindings for Windows needs attention, and it's sort of a chicken and egg problem here. There are no users, and there are no bindings, and there are no bindings, and there are no users. So we have to break this somehow. Bulk testing of Opam repository would really help to get the failures on Windows fixed and released. The nice thing about this is Opam repository now has a check for Windows when you're trying to release a new package. So you're at least aware that your package doesn't build on Windows. So the aim here is that for a developer who's trying to release something on Opam repository, right, they need not have any Windows knowledge or access to a Windows machine to make sure that something that they're trying to publish works on Windows. So that is what we mean by getting Windows to a tier 1 platform. So we have created a new repository called Papercuts. So if you're having any trouble at all trying to use anything on Windows and you don't know where to report it, please go here and report it. I'm sure one of us will look through it and try to figure out where the issue is coming from. And it would also be nice to have a central place where the issues are reported so that if there are other people who see similar build failures or issues, know that something is up and somebody is also on to fixing it. The way forward, where do we go from here? So we have a mailing list for the Windows working group, and we run meetings every month or so. You can find details about this on discuss.ocaml.org, or you can come find me. I'll tell you how to join this. If you're interested in this, it would be great to join the mailing list, and we aim to keep this going. We have some preliminary information up on this repository, OCaml Windows/roadmap, and this is where we plan to update more results of our work in the coming weeks. And the next step is, of course, to work on actual execution of the roadmap itself. So please consider contributing to this effort if this is something you're interested in. Firstly, test Opam on Windows, report issues, let us know what is not working. And yeah, if you're interested in contributing on specific things with respect to Windows and OCaml, please come talk to me, and there are also David and Casey around. Come talk to any of us. So with that, I'm happy to take questions.
We have time for 2 or 3 questions.
Thanks. So I'm personally interested in one of the things you mentioned with respect to building binaries of OCaml programs for Windows and then distributing them to users. Is that part of your immediate plans, or maybe is that something that you keep for later? I'm wondering if I should also join the mailing list and so on to learn more about that.
Yeah, you're very welcome to join the mailing list. And this is something we have heard from quite a few people. So I think that should be higher up in the priority to answer your question.
OK, thanks.
Hi, Tim Williams from Bloomberg. I just wondered what the rationale is really for supporting native Windows when there is WSL and it works so well, and that's what we use at our company, although we do use Windows, of course, on the desktop. And now that WSL supports graphical applications quite well, wouldn't it, given that we do have limited resources compared to, for example, the Python community, wouldn't it make more sense to sort of consolidate on POSIX and Linux support, and and just tell Windows users to use OCaml via WSL? What's the argument against that? Thank you.
That's a good question, and it's good to know that WSL is working well at Bloomberg. But there are a few things with that. So WSL sort of assumes, asking somebody to use OCaml on WSL, you assume that the person knows how to use Unix systems. and which is true for a lot of OCaml developers, but not so much for people who are trying to learn OCaml. They may or may not be familiar with how to use Unix systems. So you're essentially adding one more level of indirection to be able to learn OCaml in the first place. So that is one thing from my point of view. But what we have heard from commercial users of OCaml who ship products that run on Windows is that they expect the product to run natively on Windows and not ask their users to install WSL and then run whatever it is that they're running on Windows. So I mean, I'm assuming it works well in a setup like Bloomberg, where it's the same set of people who are going to use it again. But when you don't know who your user is, you're essentially adding a level of barrier if you're asking them to use OCaml on WSL.
That's fair. Thank you.
I propose we take the next question over lunch. And
Thanks.
Martin. Parti. Hello, everyone. Welcome to this second to last session of the OCaml at ICFP this year. We're going to start in a moment with my esteemed colleague, Vesa Karvonen, who's going to talk about the new POSIX.
Thank you. So in 2015, Bob Nystrom published this blog post titled "What color is your function?" And there was this idea that if you have a language with blue and red functions, and you have this problem that if you want to try to call a red function from blue function, then it's going to be a problem. And it's a problem because those red functions are asynchronous functions, and well, you just can't call an asynchronous function from a synchronous function and obtain the result synchronously. So of course, the developers of OCaml 5 knew how to solve this problem. Let's just introduce effects. And how did it turn out? Well, now we have all of these schedulers and more. I think we'll probably hear about 2 more today, who knows. And well, they are all mutually incompatible. So they all use different effects. And this means that, for instance, you cannot call EIO's IO APIs from a domain slip fiber, for example. And that's because a domain slip effect handler does not handle the EIO effects. So now we have functions of 8 different colors and counting. So it doesn't look good so far. So how do we solve this? Or what are the actual problems that we get from this is that now we're not just duplicating the effort to implement these schedulers. We have all other things, like we want to have libraries like HTTP libraries that need to do something asynchronous. And we have a massive amount of duplication of functionality. These libraries have to be ported to all of the schedulers. And this makes it really really expensive to innovate. So if you want to have a new library for concurrency, you have an idea of how to do concurrency better, then you're probably not going to have the resources to port all of the asynchronous libraries to your scheduler, basically. And naturally, no one else does have that kind of time either, so they're going to have to pick and choose, like, okay, I have this library, I want to support this scheduler, but I don't have time to support all of those schedulers. So it's naturally going to lead to a kind of community split, or even now that we have like 10 different schedulers probably, then it's going to be like 10 different competing subsections of the community. And that's not really good. So how do we solve this? And the solution that we're proposing here is that we introduce an interface between schedulers and concurrent abstractions. So the idea is that this Picos interface, it's kind of like the POSIX of effect space schedulers. So you program against the interface, and what you get as a result is kind of this picture. So in the center, we have the Picos interface, and then we have all sorts of concurrent abstractions, parallel algorithms, synchronization primitives, structuring models, and so on. And they all only depend on the interface. And on the other hand, the schedulers also depend on the interface, but they implement the interface. So they implement the scheduling part of the system. And because none of these things depend directly on each other, they only depend on the interface, then they naturally will work together. So all of these are basically like interchangeable parts of the system. You can run your code on different schedulers. You can use different structuring models in the same program, and so on. And then the question is like, what is the scheduler? And actually, we had in a previous session we had a talk about abstract data types or modules. But here's an example. Like we have a dispenser abstraction, so you can push things into a dispenser, and you can also pop things out of a dispenser. So this could be like a stack or a queue or a bag. And the thing is that this sort of trivializes the data structure. And what I mean by this is that if you have additional operations on a special dispenser data structure, like an operation that can pop multiple elements at a single operation, then if your clients using the data structure only use the dispenser interface, that they're not going to use this extra operation. So basically, we kind of have the same thing with schedulers. So what is a scheduler? If you look at the existing schedulers, then they basically have everything in them. They have the multiplexer. They have their own synchronization and communication primitives. They have probably their own asynchronous I/O integration. They have actors potentially. Maybe they have structured concurrency. Maybe they have a capability system, and so on. So what will happen with the Picos interface is that it only sort of gives you an interface to the multiplexer and timeouts. And that's basically what I think is just enough to implement everything else as libraries when you do it properly. And this will in turn trivialize the scheduler. So it moves functionally outside of the scheduler, which also means that if you have a custom scheduler, then you might implement certain things sort of inside the effect handlers. But the Picos interface actually requires certain things from the scheduler to be sort of unconstrained and to implement those constraints outside of the scheduler. That's the idea. Here's a kind of a motivating problem. What do we need to actually have in the interface to support these kinds of things? So there's like a snippet of code there, which doesn't really make sense, but the idea there is that it will basically block. So it protects a condition weight with a mutex. And imagine now that we would need to cancel this code. It's running in a fiber, and maybe we have an error in the program. We want to shut down the program, and we have to make sure that all the fibers will terminate. So there's a kind of a liveness issue there. So when we cancel this, we really want it to sort of terminate, so it has to unwind everything. But there's also a safety issue, like if the fiber happens to be in the condition weight, and then we cancel it, then it has to reacquire the mutex, because the protect function will unlock the mutex at the end of the scope. So we need to be able to address these things. Here's another example using kind of structured concurrency thing. So the idea is that we have a program that allocates some resources, and then we have this protected block where we have some sort of finalizer. It deallocates or frees the resources. But we also use fibers there. So we create a scope for fibers, and then we create or fork new fibers, which probably use those resources or may use those resources. And then what happens if this gets canceled? So what we need to make sure that actually when we execute the finalizer, then all of the fibers that might be using the resources, they have to be terminated properly. So the join after function there, it really has to wait for all of the fibers to terminate properly before it allows to return. And then the finalizer will run as normally. So these are the kind of motivating problems that I had. And now we're ready to go to the actual architecture of the interface. So it's basically based on a trio of abstractions which work together. And first of all, there's a trigger abstraction, which allows you to basically await for a signal from some other fiber or thread or domain or whatever. And then there's a computation abstraction, which basically allows you to sort of both observe and sometimes control an asynchronous computation. So it basically has a state, either it's running or it has been completed. And then there's the fiber abstraction, which gives an identity to independent threads of control, and also allows those fibers to control certain aspects of how the scheduler should work with them. And in a bit more detail, here's like an extract from the trigger signature. So we can see that it's a simple monotype. We can create triggers, and the idea is that you can then insert that trigger into some concurrent data structure, and then some other fiber or whatever can find the trigger from there and signal it. And we can also, as the owner, we can await on the trigger. And the idea there is that if the trigger has been signaled, then that will just return immediately. Otherwise, the scheduler will suspend the fiber, and eventually it will return either with none, which means that the trigger was signaled normally and the fiber has not been canceled. But otherwise, it might return with an exception and a backtrace, meaning that the fiber was actually canceled. And regardless of which outcome you get, you have to clean up after yourself. So if you inserted triggers or modified data structures, then you have to make sure that you clean up everything afterwards. The computation abstraction, on the other hand, it does carry a value. And you can create it. It will be sort of empty in a running state. And it's possible to return a value to it, which turns the computation into completed computation. But you can also cancel it with an exception. And it's also possible to check like whether the computation has been canceled or not, but also to await for the computation to finish, and it will either return the value that was returned to the computation, or it will raise an exception. And what's more interesting, though, is that it's possible to attach triggers to computations. So that allows anyone to observe the state change from running to completed of a computation. And then there's also the operation for timeouts, which we'll not get into in more detail here. A fiber, the fiber module provides some important operances, like the ability to yield. This just asks the scheduler to reschedule the current fiber. But more interestingly, we have the fiber type, which again doesn't carry a value. We can ask for the current fiber. So if you're running code somewhere and you want to figure out what's the current fiber, you can ask it from the scheduler. But you can also create new fibers and spawn them on the scheduler. And the fiber, interestingly, has a couple of pieces of state. It has a computation. So every fiber has a computation associated with it, which can be manipulated to set up scopes for cancellation. And you can also manipulate a Boolean flag, which tells whether the scheduler should propagate cancellation to the fiber when it performs effects. And there's also fiber local storage for extensions, which we are also not discussing today. So the cancellation protocol is fairly simple. So the idea is that every fiber is always associated with a computation. And when you await for a trigger to be signaled, the scheduler attaches the trigger to the computation associated with the fiber. So what that means is that if the computation is completed, canceled, or returns, then the trigger will be signaled. And that allows the await to unblock, and the fiber will basically then terminate. And all of this is implemented partially, so it's like an abstract class, and the way the missing things are implemented is through effects. So we have these 5 effects: await, cancel after, current, yield, and spawn, and these are to be implemented by the scheduler. And one of the contracts here is that the interface does not dictate which fiber to run next. So after any effect, the scheduler can decide which ready fiber to run next. And that's basically all. So of course there are contracts between the interface and the different parties, and there are also like additional operations which help. But basically, because it's all about cancellation, so about setting up contexts where you're expecting cancellation, and also reacting to cancellation. So what can you actually implement with this interface? And we have actually implemented quite a few examples. We have, with the Picos repository, we have 4 different schedulers. We have a single-threaded scheduler, a multi-threaded scheduler, and then there's a randomized scheduler, which actually, after every effect, it randomly picks 1 fiber to run. There's also an interface to LWT, which doesn't really implement its own scheduler. It just runs everything on LWT directly. And there's also a scheduler called Moonpool, which has been ported to use Picos by Simon Kuanes, also known as C-Cube. We also have a synchronization and communication library, which has a standard library style, mutexes and condition variables, semaphores, a lazy module, an event module, and a few other things. And there's also a library for resource management, which interestingly has this ability to move resources from one fiber to another and do it safely so that there's no leak. And there's also a sample library for structured concurrency. There's also an I/O library using only the Unix module that comes with the compiler distribution. And there's also a simple minimalistic implementation of this co-HTTP library for Picos. And there's also an experimental tiny HTTP daemon also by C-Cube. And yeah, so basically you could already write some applications with these. So here's actually a kind of toy program, not very interesting. We'll go through it very quickly. So it just basically forks 4 fibers. And here it actually uses the standard library version of Unix Sleep, which basically blocks the whole thread. So the scheduler cannot do anything while the thread is sleeping. And then it obtains the domain index, and then it prints the domain index, basically. So the mutex is here used mostly as an example. So yes, there's a mutex. And also it helps to make sure that the output isn't garbled. So we can then run this program on pretty much all of the schedulers. So we could run it on the single-threaded FIFO scheduler. So we can see that it runs all the fibers on the same default domain, basically. And then we could run it on the multi-domain FIFO scheduler, which actually runs all of the fibers on different domains in this case. Then there's the randomized scheduler. Again, uses multiple domains. And then there's also the LWT scheduler. So we can actually run this program already on multiple schedulers. So we have sort of validated that we actually have the situation that we saw in the dependency picture, basically. So it should be clear now that Picos is not a scheduler. It's at least much more than that. Here's another example. So we start with a couple of libraries. And then there's not very interesting stuff here, but this is basically like a client that posts a name to the server, and then the server responds with a body that says that hello something. And more interesting is the setup. We create this socket for the server, and we use the resource management library there so that we make sure that the socket will be closed eventually. We set up the socket. We make it non-blocking because that's much faster, basically. And we create this scope for fibers, which we terminate on return so that we can sort of automatically clean up things or terminate things. We create this fiber for the server. And then we create another scope for fibers where we run the clients in separate fibers, basically. Or we actually run, Oh, I must have forgotten, actually, there should be a fork there. But yeah, it basically runs the client code multiple times. And then we can, of course, run it with different schedulers. So here's just an example using the randomized scheduler. So we can see that it already handles the responses from multiple, using multiple domains, basically, running things in parallel. So yeah, what's missing is that this is just a sample. We could just as well be using libraries written by someone else if they just use the Picos interface, and we could use the same schedulers or different schedulers and so on. So everything is interchangeable and interoperable. So the interesting question then is, what about performance? And I should note that I mean, Picos by itself, it's designed to be unopinionated. So it doesn't require you to use structured concurrency, for instance. And it has support for this parallelism safe cancellation, which is not supported by all the schedulers. It doesn't require I/O to be done in the scheduler loop. Some of the schedulers do that currently. And well, I have paid a lot of attention to performance. So first of all, here's a data point on memory use. So as an example, EIO currently uses about 504 bytes per fiber. With similar features, Picos takes between 160 and 312 bytes, so quite a lot smaller. And basically, the 160 bytes is probably closer to what is the most common use case. And also, this would actually be a little bit smaller because I think that the standard library allocates an extra closure, which wouldn't really be needed. And so we could get rid of that, and it would reduce that to 128 bytes per fiber. Also, I ported a few benchmarks. It's a bit difficult to compare different things with benchmarks, but there's, for instance, a yield benchmark. So with EIO, yield takes from 190 nanoseconds to 950 nanoseconds on this particular benchmark machine that we use. The Picos 5.0 scheduler takes 130 to 330 nanoseconds, so it's quite a bit faster. There's also a semaphore, which is specially implemented in EIO, and we also have this semaphore implementation for Picos. And again, the Picos version is quite a bit faster, but of course, this is a bit like an apples and oranges comparison because the semaphore implementations are quite different. And the EIO implementation, it uses a very sophisticated data structure and algorithm, but it has not been optimized really carefully. There's also, I mentioned the tiny HTTP daemon, so there's a, it was benchmarked to be able to do like 500,000 requests per second on a rather beefy machine. On other machines, not necessarily performing that well. But the bottom line is that this should allow pretty efficient concurrency. And to end, so basically today, schedulers are deep. So they have their own implementation of everything. So it's going to be thousands of lines of code, and then all the extra libraries that you want. That's tens of thousands of lines. And with Picos, a scheduler can be like 100 to 500 lines of code. I mean, it's basically just a data structure and loop. Like I said, Picos trivializes the scheduler, so it's not unbounded complexity. It's just the multiplexer and timeouts. And then we can do all the other things as libraries, and they are fairly modular, simple things. Don't take a lot of code. So we get basically like all sorts of interesting combinations of things quite nicely. And in the future, maybe we actually don't want to talk about schedulers. We want to talk about concurrent programming models. So you want to use actors to structure your concurrent code. So maybe you have some sort of collection of things that work with a nice actor model, or maybe you want to use capabilities, then you have maybe a different collection. Maybe you want to use more traditional concurrency. There's maybe another collection of things that work with any Picos scheduler. And we could mostly share most of the other things, like the multiplexers, for instance. They are not probably the most interesting part to innovate on. So we can basically then combine these very freely. And this is probably much bigger change than what might be obvious, because this basically potentially eliminates the whole competition. So there's no need to compete or create like completely incompatible ecosystems. We could just work together. And here are some next steps. We're going to, of course, continue development of the Picos system. And yes, more is more. Thank you.
Thank you, Vesa. I'm sure you all have a lot of questions. We have time for a bit. Come here to ask them.
Given that EIO is also worked out at Taradas, I'm curious if there's been any efforts to move EIO to be based on Picos so that it would be interoperable with other things that way.
Yes, that has been planned to happen. So I believe Thomas will look into that in the future. So hopefully it will be ported to Picos.
One of the things that was not clear to me is the goal is to actually be the most efficient implementation to be used as a core, or to be like an actual standalone library that end application should use.
You mean the core library? Is it like? So the idea with the Picos interface library is that it provides you with this trio of concepts, and they are very low-level things which are designed to be to have like a very small memory footprint, but they're not designed to be necessarily like easy to use, for instance. So the idea is that you can implement then more interesting higher-level models efficiently on top of them. So that's the idea.
All right, I think that's it. Let's thank Vesa again. All right, our next talk will be remote work from, I mean, two people who I think are in this room, which are Gabriel Radan and, no, Ludovic is not here. And Wenkedu, who, yes, is right here, remote. Is everything working?
Hello?
It seems to be working well.
Okay. Can I begin now?
Yes, we can hear you. You can start.
Okay. I think. Oh, there's an echo from your channel. So hello everyone, I'm Wink. In my talk, I'm going to talk about distributed programming in OCaml based on the actor model. This work is did for my master internship. So I'm under the supervision of Ludovic and Gabriel. So the objective of this work is to allow distributed programming in OCaml based on the actor model. So in this talk, first I'm going to talk about what is the actor model and the library to manipulate with actors, and then is the implementation we need to support the distributed programming, and then I will talk about the runtime architecture of this implementation and the compile time implementation. So what is the actor model? So in the actor model is a model for concurrent programming. In this model, we are programming with an entity called actors. Each actor has a private state, and it has some asynchronous messages and they are often implemented by features. You can see here in the graph that we have two actors that are sending each other messages. And when one actor receives messages, it will trigger a function to be executed by a scheduler inside of it. The scheduler will schedule this message to be executed asynchronously, and this message will access to the private data, And each actor is bounded to one particular logical thread. So in this model, we have the advantage of data risk freedom. And how are we gonna define actors in our code? So here in our pastel code, we first declare the name of this kind of actors. Here is a counter. And then we specify in the code that we have two private states, which are X and Y. And then we will specify what kind of messages this counter can receive. And in our case, it's the increase and the decrease. And inside of each messages, we will implement we will write the implementation. So in practice, how we're gonna write them, particularly in OCaml. So here is the code that using the OCaml object feature to define actors. So here is the same that we define a counter actor, which we using the object attribute for the private state, here the X and Y. And then we will use the object method to define their messages. And here is also the increase and the decrease. But here, as I said, that the method will be executed asynchronously. But here we only write synchronized code. So this here at the beginning, right after the class, we have a PPX extension point that will transform all the method of this object to make them return future. And when this method gets to call, it will be put into a scheduler. So after to create an actor, what we need to do is to use the new keyword to create that actor with the initial argument. And then we will able to send messages to actors using the object method. And here is a program that written by that based on actor model. So we have many actors sending each other messages. So here it will be the object method calling to each other. And this call goes through memories. And to extend this kind of stuff to distributed programming, what we need to do is only to put box around actors. Because in the actor models, each actor do not have shared memory access between actors. So it means that the actors can be located in different physical memory. Also, the method call between actors are asynchronous. So it means that the call can go through networks. So this allows programmer to transparently programming in distributed system. And to implement, to support such kind of stuff, we need to implement a runtime system to support all the operation I said before through networks. And then it turns out that this runtime system needs some meta information from the programmer defined code. So we have a PPX extension that will be executed statically to analyze the programmer write code and to generate the metadata for the runtime system. And here is the implementation. Here is all the implementation we need for this distributed system. The first, we need to support creating an actor in a remote node, and then call method of a remote actor and get the future of that ongoing computation. And then later, we will be able to query the result of that computation based on that future object. And then in the distributed system, we'll be able to share actors and futures through the system. And here I'm going to talk about the point 2, 3, and 4, because we don't have that much of time. So here is an example of how to remotely call actors in the distributed system. And at the line 2, we will, after creating an actor, which is a counter, and at line 3, we will call its method by the object method. And later, we decide to encourage the result of that call. So to implement this, when the method get called, when we execute that method, after creating the counter, we will be able to get an instance identifier for that counter. And we will generate a call ID for this remote call. And then we will send all the necessary information of this call through network, including the method name and also the arguments that we apply for this call. And when the node 2 receives all the information, he will be able to identify the original actor that was instantiated before here. So he will execute the code. And then when the computation finish, he will actively send results back to the node 1. So that's why you can see here they are using two different connections for communication. And we're back to node 1. When after sending the request at node 1, the node 1 will generate a local future entity represent that remote call. And this local future, the state is based on the result of the node 2. If a result has been sent back from node 2, the future will be ready. Otherwise, we will wait for it to synchronize, or we will use the cooperative scheduling. And then is another case that how we're going to share actors in the distributed system. Here is an example that we have two actors. Another one is the downloader, which requires a counter at the beginning, and when he downloads from some stuff, he will increase that counter. So you can see here in the line 9 that when we create this downloader, we need a counter. We need a counter. So how we gonna? You can see here that these two actors are in different nodes. So how we gonna serialize the counter to the node 2? So it turns out that we cannot copy all the binary data of that counter through network and reconstruct them on the other side. Because first, it's not possible practically, because actor has a scheduler and it has some ongoing computation, so it has some many continuation and closure. It is impossible for us to copy all of them. And secondly, based on the actor model semantic, we should not copy them. One actor in the model representing one execution thread with ongoing computation. So when we share actors, what we are actually sharing is a reference to that actors. So it means that we will apply special serialization policy for actor objects. So you can see here at node 1, after creating two actors and passing the first one to the constructor of the downloader, we will serialize the first counter to a counter descriptor, and we will send them back. We will send them through a network to the node 2. And then at the node 2, he will be able to reconstruct a mock counter based on this descriptor. What is a mock counter? Mock counter is a kind of mock actor. A mock actor has the same method as its original actor, but all the implementation of their method is just sending request to the original actor. So after we reconstruct a mock actor at node 2, the subsequent sequence will be the same. We're just creating a downloader and do the stuff. So, and about the future, it's the same, that we will apply special serialization for future objects because we cannot copy them. And that is the architecture for this runtime system. As you can see before that in the distributed system, each actor has some I/O operation to other node. So we decided to centralize all the I/O operation to one special thread, which we call proxy thread. This will improve the efficiency of the node. And this proxy thread will use the concurrent I/O to manage all the network operation between nodes. So actually, the request between nodes are the request between the proxy thread of that node. And also, the proxy thread will also serve to manage the state of each node. It has many tables, like what are the actors in that node, and what are the calls we have sent before. And the communication between actors and the proxy thread is through memory and through a queue. So that is the compile time implementation. For example, when we create an actor remotely, for example, the programmer at node 1 want to create an actor at node 2. When we actually create that actor at node 2, we need to find out the constructor of that actor. But in OCaml, we cannot write code like a class and get a constructor to reflecting the constructor that the programmer defined before. So we need a runtime reflection to get that constructor. And it is same for the actor method, that when we remotely call a method, even we know the name of that method, we cannot using that literal value to getting that to execute that method. So we also need to build a reflection mechanism for this kind of stuff. And also, as I said before, that mock actors and the mock class has the same method of the original actors, but with different implementation. So we, at the compile time, we will analyze the original actors and generate the mock actors and the mock class. So the general step to implement this is that by the person actor extension point, we will able to inspect the structure of the class, and then we will insert the metadata we need. And then eventually we will insert some code at the beginning to initialize the runtime environment. All this is done by the OCaml PPX. And in summary, we have delivered a library that is based on actor model for distributed programming. It allows create actors remotely, call actor method remotely, and query its results. And also in this distributed system, we can share actors and futures. And this library abstract away all the network details. But unfortunately, there are something we did not accomplish. That is, this library is not fully transparent for distributed programming. The programmer must explicitly mark the data type. That is why, as I said before, we apply special serialization policy for actors and futures. But unfortunately, we cannot distinguish the variable at runtime if it's an actor or a future or a value. So we need a programmer to explicitly mark them for us, and we can apply proper serialization. And this library is available in this website, and the example I shared before is available at the examples folder. And that is all of my talk. Thanks for listening.
Thank you. I think we have some questions.
Yeah, let's say that I send an actor an RPC and a cosmic ray flips a bit in its memory and it crashes, and so that RPC is going to return an error. Does this framework have any built-in error handling mechanisms or error recovery mechanisms? Framework have any built-in error handling mechanisms or error recovery mechanisms?
Sorry, you did not turn on your micro, so I do not listen your questions.
Can you hear me?
I saw that in the live stream. Sorry, you did not turn on your micro, so I do not listen your questions.
Can you hear me?
Sorry?
Do you have any error handling mechanisms or error recovery?
The Discord account in the session, its micro is closed.
Sorry, Wenk. I mean, the audio is not working very well, so I'm going to answer. No. More seriously than that, we try the minimum, but implementing error recovery in a distributed system is a big task, and so we didn't take the time to do that.
There's another actor framework called Riot. How does this work compare to that? And have you thought about collaborating so that we can have one implementation rather than multiple?
Yeah, so the objective of those two libraries are pretty different. So Riot implements the runtime actor, so Erlang style, I would say. And this, so we worked a lot for the distributed part, but the basic idea was to have the programming style in Scala-like actors. And so that, yeah, in practice, those are two very different programming style. I would hope that eventually everything will be based on Picos, and then we can share everything. Yes, eventually I want to do that, yes.
And yeah, and I have, I guess, a beginner question about actors and the actor model. Could you give like some examples of the kind of applications it's good for or convenient? Like if I want to write a distributed application, what would be a good fit for that?
So basically, actors are pretty good when you need task-based parallelism with internal state. That's the main thing it is good for. So things that are a little bit big, but that can be shared. So yeah, that's the main idea. So you can think of, for example, actors that will delegate some work to sub-workers. Yeah, these kind of things, depending on your on how efficient we can make it. You can think of coarse-grained computations. So yeah.
Okay, thanks.
All right, thanks a lot. And now we have Stefan Muller, who's going to talk about domainslib and a new extension of domainslib. Oh, he's right here.
All right, thanks. So similar to the last two talks, I'm in a setting where I want to use lightweight threads, so something like what's provided by domainslib, for concurrent or interactive applications. So one place where you might want to do this, I didn't coordinate the motivating example with Vesa, but we ended up in similar places, but with a slight twist. So let's say you're building a small web server. I want to have one big loop that accepts connections. And then let's say I want to handle each client in a separate thread. So whenever I accept a new connection, I spawn a new thread to handle that connection, and that takes in those requests and then gets garbage collected when the connection is closed. The twist is, in the background, I want to do some analytics. And maybe what I want to do is I want to check the request log and maintain a list of hosts that are bad. Maybe they're performing too many requests, and I think they're trying to perform a denial of service attack or something. So I have another loop that runs in the background and trawls over the request log and tries to classify these hosts. So maybe it also wants to do this in parallel. Remember, I have a lot of threads I can use. So it takes the request log in parallel, spawns a bunch of threads that do this computation, and then report back. So there is shared state here. So for one thing, the connection threads place the request in this buffer, which is then handled by the classification loop. And then once the classification loop classifies hosts into good or bad, it stores that in a big hash table that obviously needs to be read by the accept loop so that we can actually ban the hosts that are classified as bad. So one thing that comes up immediately if you try to program this is that I've been saying we have these threads in the foreground and we have these threads in the background. But these fine-grained computation libraries like domainlib, fine-grained parallelism libraries, don't really have a notion of priority on these lightweight threads. And that's really something that becomes vital here. So in particular, let's say we have 3 priorities and we want to prioritize handling existing connections over accepting new connections. So we'll handle existing connections at the highest priority, we'll accept new connections at a medium priority, and then do the classification work kind of in spare cycles at your lowest priority. So with that motivation, I've built an extension of domainslib called priodomainslib, which extends domainslib with these priorities on tasks. So this is following up on work that's been done in a parallel variant of standard ML and also by some collaborators in Silk. So now bringing this to OCaml. So what needs to change to add priorities? Well, obviously the thread interface needs to change because when you spawn a thread, async a computation, you want to be able to specify the priority. The scheduler needs to change because the scheduler needs to respect priorities. We also want to have mutexes. We have global shared state. We need to protect that. And it turns out we need a new mutex implementation that also respects priorities. So I also have some design goals. One is that it should be a conservative extension of domainslib. I want existing code in domainslib to just work in priodomainslib at one priority. So if you don't specify anything with priorities, we'll assume that you're just running your computation all at one priority, and it should just compile and work. So it should be compatible. The other thing is that I wanted to support an arbitrary number of programmer-defined priorities, as opposed to, say, the POSIX priorities, which is specify a number between 0 and 100, what the semantics of priority 42 is, as opposed to priority 85. Good luck. That's up to you to figure out and remember, and also coordinate with everybody whose modules you may be linking with. So we'd rather have them be programmer defined, and you sort of define the number you need and assign them your semantics. The reason that we need a new mutex implementation is that once you have mutexes and priorities, you can have the problem of priority inversion. I'll go over that a bit later in the talk. Speaking of what I'm going to do in the talk, so I'm going to briefly go over the API, motivating it using examples from this web server example. I'll talk briefly about the design of the scheduler. I didn't design a new scheduler for this, mostly using an existing one, but I'll talk about some of the challenges in implementing it in OCaml. And then just the status and yeah, talking about the challenges that I've run into and possibly how to solve them. So we need an interface for priorities. So the priority module defines a new type of priority. So priorities at the moment are totally ordered, but you define them as you need them. So there's this function new priority, which creates a new priority. And so every time you call this, you get a priority that's higher than all of the existing ones. So you define your priorities from bottom priority to top priority, and you can also get the count of how many you've defined and get the top priority and the bottom priority and so on. And there's also functions that I haven't shown for comparing the ordering of priorities. So priorities here are first class values in the system. So in our web server example, we have 3 priorities. The lowest one is this priority that we use to classify the hosts in the background. The middle priority is the one that we use for this loop that accepts new connections. And the highest priority is for serving existing connections. So each of those is just a call to new priority. Here is the updated task API. So if you're familiar with domainslib, the top 4 functions or definitions will look quite similar, with the exception that async now has an optional priority argument. So the use of this as an optional argument means that we're compatible with domainslib. When you async a new thread, you can specify the priority, or optionally, if you don't specify it, it's assumed to just async at the current priority. And if you haven't defined any new priorities, that priority is just the single priority that exists in your system. So we're still compatible with domainslib code. Oh, sorry, 3 of these functions will be familiar. A new one is that a thread can change its priority. That one, the priority is not optional. You can also, 2 of these 4, sorry, are familiar from domainslib. And you can get your current priority. The await, which takes a promise and waits on it, is totally unchanged. So the way you await on an async thread, you just do that exactly the same way. At the risk of creating yet another incompatible asynchronous I/O library, we also want non-blocking I/O functions. Ideally, this would be integrated with Picos at some point, but I just learned about that 20 minutes ago. So at the moment, that's built into the library. So the way this is used in the web server. It's just a snippet of code. We've accepted a new connection. We want to atomically increment the number of connections we have, add it to the list of some connections that needs to be cleaned up at the end. And then we want to asynchronously spawn a new thread to serve that connection. So we'll do that by spawning a new thread at priority serve B. So otherwise, this looks very much like code you could write in domainslib, just with that optional priority argument. And then we go back around and continue accepting more connections in the accept loop. OK, so as promised, I need to talk about mutexes. So we have two kinds of global state. In this web server example, we want to protect it with mutexes. We have priorities. What goes wrong? So very briefly to introduce the priority inversion problem, let's say that you have a low priority thread that tries to acquire a lock and succeeds in acquiring it. And now suddenly a high priority thread comes along and attempts to acquire the same lock. The lock is held, so the high priority thread goes to sleep. So we could already call this a priority inversion, because there is a high priority thread that's doing something very important, but it's blocked on a low priority thread that's doing something presumably less important. This is what's called a bounded priority inversion, and it's generally not considered to be as much of a problem, because hopefully quickly, if the code is well designed, the low priority thread will get through its critical section, release the lock, and the high priority thread can go on its way. The problem with this is that it can quickly become an unbounded priority inversion if we simply, after the low priority thread acquires the lock and the high priority thread attempts to acquire the lock unsuccessfully, let's say a medium priority thread comes along that runs, let's say, forever, and blocks the low priority thread from running its critical section and releasing the lock, which means that the high priority thread is really now sleeping on both this low priority thread and this long-running medium priority thread. So this is really where priority inversions become a problem. So there are a number of dynamic protocols for dealing with these priority inversions. The one that I implement in PrioDomainslib is called the Priority Protection Protocol. So it's very similar to a related protocol called priority ceiling, where each mutex is assigned a priority ceiling, which is the ceiling, the highest priority at which this mutex may be acquired. So going back to our example, the low priority thread tries to acquire the lock, acquires the lock. The lock now is green. It's specified with this high priority because the high priority thread also tries to acquire the lock. Now, with the priority protection protocol, when the low priority thread acquires the lock, it actually becomes a high priority thread. So it is immediately promoted to the priority ceiling of that lock. So it proceeds through its critical section as a high priority thread, which means it has precedence over the medium priority thread, and it unlocks the mutex, which can then be acquired by the high priority thread. So we don't have this priority inversion. Just to show how this works in the web server, we have these two pieces of global mutable state. We have the request buffer, and we have this hash table of bad hosts. So we have two mutexes to protect each of those. And they have two different priority ceilings. So the priority ceiling, just like with async, we have an optional argument that specifies the highest priority, or the priority ceiling. If it's not specified, the priority ceiling just defaults to the highest priority that exists in the system. So the request mute protects access to the request buffer. Now this is only ever accessed by the classification threads, which are low priority, and the serving threads, which are at the highest priority. So this priority ceiling needs to be at the highest priority. On the other hand, the bad mute, which protects this bad hosts hash table, is not touched by the threads that serve connections. It's only touched by the thread that it accepts new connections, which is at this medium priority, and by the low priority background threads. So we can specify a more conservative priority ceiling for this. We can say that it's not acquired by the high priority threads, only by the low and medium. And so threads acquiring this lock at a low priority are just promoted temporarily to medium. So when we lock and unlock this mutex, basically we don't need to change what we do. So the priority stuff only comes in when we create the mutexes. We need to specify the priority ceiling. I want to talk briefly about the scheduler design. So for more details, see this paper, which gives the details of the prompt iSilk scheduler, which is what I've implemented. I'm just going to go through very briefly how the scheduler works and how it's different from the standard domains-lib work-stealing scheduler. So as with standard work-stealing schedulers for lightweight threads, like the existing scheduler in domains-lib, each worker has a concurrent work-stealing double-ended queue. So we just use the work-stealing queue implementation from Saturn, which domains-lib also uses. I see the next talk is on Saturn, so I won't say too much about that. In prio domains-lib and in prompt iSilk, we no longer have one of these per worker. We actually now have one per worker per priority. So as with standard work-stealing, when you decide you're working at a particular priority, I'm not going to go into too much detail on how you decide which priority you're going to do work at, but intuitively you want to work at the highest priority that you can. So see the paper for exactly how that's, at least the heuristic for how that's approximated. So you pop a task off the queue for the priority that you're working at. Each worker does this concurrently. When a worker finds that that deck is empty, so it is unable to find new work locally in its own queue for the priority at which it's attempting to do work, which is maybe the highest priority, it becomes a thief and it tries to steal work from another worker. Unlike in traditional work-stealing algorithms, which then do this randomly, randomly choose a deck from another processor to try and steal work from, prompt iSilk actually maintains a queue of decks, again, a queue of decks at each priority. So instead, we'll go to the high priority stealing queue. We'll take the first deck off of that queue, steal from it, or indeed, under some circumstances, if we're able to, we might actually just take that entire deck as our own if somebody else isn't currently using it. I don't want to go into the details on that. But at least we will steal from that and then push it back on the back of the queue. So in this way, rather than randomly steal, we kind of round robin who we steal from. And that reintroduces a lot of the nice aging heuristics that you get from randomized work stealing, but that would otherwise not actually hold if you just naively do kind of one randomized work stealing instance at each priority. All right, that's all I have time to say about the scheduler. So I want to talk briefly about the implementation status. So I've implemented this as a fork of domains-lib. I've implemented a few small micro benchmarks just for testing pieces of the code, and I've also implemented this web server benchmark, tiny web server, about 300 lines of code. Haven't really done a lot of quantitative evaluation of prio domains-lib yet, so that's still work to be done. There was one experiment that the reviewers very reasonably requested, so that I wanted to just at least give some very preliminary numbers for. So I just got these numbers quickly before getting on the plane. So this is still a preliminary experiment, but the idea is to see if we have just code at one priority, so code that's compatible with, say, existing domains-lib code, and I run it under prio domains-lib, what's the overhead with respect to vanilla domains-lib? So as you can see, there is quite a bit of overhead currently. This is the Fibonacci benchmark from the domains-lib test suite. On 4 processors, domains-lib is getting about 2.5 times speed up. Prio domains-lib is getting about 1.75x speed up. So as you can see, there's quite a bit of engineering work left to be done on the scheduler implementation. But at the moment, that's still work in progress. So more fundamental kind of challenges. So long-running sequential threads at a lower priority need to call yield. So ideally, if we have a processor working on a long-running low-priority thread, the scheduler would preempt it periodically to check if there is any higher priority work that it should be doing instead. Unfortunately, this isn't possible in the current multi-core OCaml runtime. And this, I found an issue from November 2016 complaining about this, and there was some discussion, and then it was closed. This would be really nice, but I feel like if KC was asking for this 8 years ago, I don't know what chance I have. The other problem, so the priority protection protocol is kind of nice. That's the one that we implement currently for preventing priority inversions. It would be nice to give some options as to the protocol that's used. For example, a more common one that you hear about a lot is the priority inheritance protocol, where you don't immediately promote threads to the priority ceiling. You do it a little bit more lazily. That would require dynamically changing the priority of another running thread, which requires kind of more explicit handling of thread objects than the current domains of implementation does. And I think it would be hard to do that conservatively. I tried a bit. It proved to be pretty difficult. Similar to the kinds of problems you run into with cancellations. So I suspect doing this with Picos might make that a little bit easier as well. So with that, the preliminary implementation is on GitHub, so I invite you to take a look, and I'll take any questions.
Thank you. I'm sure we have questions in the room. I have a question from Gabriel Scherer on remote, who says, it's not clear to me what are the expected benefits of adding priorities to our code due to my lack of experience with this sort of concurrent programs. Certainly throughput is not going to benefit, maybe it will get slightly worse. I suppose that priorities are designed to reduce latency for some of the computations at the cost of increasing it for others. How do I measure, how do I measure that my priority assignment are achieving the desired result?
Yes, so the measurement problem is interesting. The intuition that I want to kind of give is that you have some threads where throughput is the goal and some threads where latency is the goal. And so, for example, in the web server, for the classification threads, you are willing to give up a whole lot of latency for better throughput. For these foreground interaction threads, maybe you're willing to give up some throughput to get better latency. So the threads just have different requirements. Tuning exactly what priorities you want to give each thread to get the best latency throughput trade-off for each one is complicated. And I've also thought a lot about how to measure this, and measuring it is not easy. Once you have more of a gray area between threads that only care about latency and threads that only care about throughput. But if that's your metric, then it's pretty clear what the right trade-off is. And so you want threads that really care about latency to be high priority. Threads that don't care so much about latency can be lower priority. So I've talked about this in the context of a concurrent interactive program. Even if latency is not the issue, even in purely computational applications, you may still want priorities. So an example is if you're implementing something like A*, some kind of search that's guided by a heuristic, you can, let's say you want to expand a node and you go every direction in parallel. The more promising directions based on your heuristic, you can give those a higher priority. And so then the scheduler would just under the hood, without you doing anything else, prioritize those higher priority neighbors and potentially avoid, find the goal faster, and maybe even if you're searching in an infinite tree, you might actually avoid non-termination by prioritizing the high priority or most promising neighbors.
I would have a question about the mutex modification that you did. So obviously for domain sleep, you had to modify domain sleep to introduce priorities. I'm wondering how many modifications you have to do to Picos in order to support priorities. So let's say you've got a Picos application that interfaces through domain sleep, and it uses a mutex that doesn't know about priorities. Can you like assign a default priority to that one and still interoperate correctly with it?
Yeah.
Or do you need to make too many modifications to the interface?
I suspect you would have to. So the mutex implementation really has to know about priorities. And so I suspect if you were trying to combine this with a mutex implementation that is provided by a different scheduler and doesn't know about priorities, I suspect that wouldn't work. So I think you might need either to restrict the set of modules that you can interface with to only those that know about priorities, potentially even actually build in some notion of priorities to Picos or whatever framework that you're using. I would need to think more about exactly how much modification would be needed, but yeah, definitely some.
Yeah, so currently Picos does not have a built-in notion of priority, but it's something that I have thought about. And one way to do it is to actually use the fiber local storage to store a priority for fibers. And then you can have schedulers that will be able to inspect that priority from the fiber local storage. But then you can also have mutexes that also know about the priority and so on. So it should be possible, although, of course, there's limits, like if you have teams that don't know about priorities, then they don't care about those, of course.
We should talk.
I have a clarification question. So in order to, when you promote a thread from low priority to high priority when it's for the locking, is it still bound to the ceiling of the mutex? Like, is a low priority thread still able to lock something like after the promotion?
Is it able to lock, once it's promoted to high priority, can it lock something of lower than high? No. So that would be an error. So once it's been, if it's in a critical section of a mutex with a high priority ceiling, it's going to run that at high priority, and then so it then can't try to acquire a mutex whose priority ceiling is medium, for example.
I see. Thank you.
Sure.
Thank you. For the last talk of this session, we have Karine Morel, which is going to talk about the stars.
There's Clément as well. Right, so I've been working in Saturn for quite some time now with Vesa and a few other people, so I'm going to talk about our work in Saturn. And then Clément will talk about what he's working on, which is verifying Saturn data structure. So Saturn is a collection of concurrent safe data structure for OCaml 5. With OCaml 5, you have this new type of concurrency, like competitive concurrency, where you can have multiple threads or multiple domains, as we call them in OCaml, that are working in parallel. And the thing is, implementing a data structure is not easy, right? Like writing an hash table is not something that is pretty hard. And when you try to do that in a way that this is going to work with multiple domains, trying to access this in parallel, then it kind of becomes a mess. It's pretty hard. And so the intent behind Saturn is to avoid you this mess, is to provide some already well-tested benchmark, optimized and even verified concurrent safe data structure. And so when I was writing this slide, I was like, well, they are probably not going to take my word for it. Maybe I need to show them something that shows that this is hard. And so I what I did is that I went on GitHub and I searched for the word atomic in the code written in OCaml. Because when you are using the atomic module, you are probably trying to do some multi-core programming. And I stumbled on this implementation. No shame on the author here. It's, the whole point of that is to show it's not easy to do, and I try to anonymize it. So the idea is that the author needed a queue with a size function, like a function that gives you the number of elements in the queue. And we don't have that in Saturn. Like the queue don't have a size function because it's actually pretty hard to do. But the author tried to do it the way you will do it in a sequential way. So they define a type T, which is a record with a size and the queue. And the size is an integer that is going to be accessed by multiple domains, so it's protected under an atomic. And the queue comes from, supposedly, concurrent safe library, so Saturn. So nothing to be done here. And then you do something, or like the things that you will expect to do. So when you push, you increase the size. When you have a pop, if you find something in the queue, you decrease the size. And if you find the queue to be empty, you reset the size to 0. So nothing is illogical here, right? But if you try this test, it's actually going to give you some surprising result. So this test, you have two domains that work in parallel. One is doing one pop, the other is doing one push, and once they are done, you do one additional pops. So at this point of the code, your queue is empty, so your size should be 0. But if you run it 10 to 20% of the time, you are actually going to get a size of -1. And if you look at where the author was trying to do here, he was just trying to add a size function, which is something very basic, right, to a very common data structure, a queue. So something that looks very easy to do, and still there is a mistake in it. And even worse than that, you could have written this test and never saw the bug. And this test is specifically written to catch this bug because I knew about it. So in a real application, you will probably have written a more general test and never find this bug, or maybe once, and then have a hard time to actually reproduce it. So this is one of the main reasons why this is hard to do that. But you might have already know about it. That is what hard to do. So maybe when you are writing a concurrent data structure, you go to the literature and you try to find algorithms that do what you want to do. So you could do that. For example, if you search for a trade safe stack, you will find the Trevor stack. It's a pretty simple implementation to do. It's not a lot of line. It's basically just stating that stack is an atomic list. So no need to look at it, it's working. It's perfectly fine. But if you are trying to do that, it's probably because you are trying to do some multi-core programming, so you are probably trying to have some good performance. And so this is a benchmark of what I call an atomic list, which is just the Trevor stack. So in this benchmark, you have just one domain that are working in parallel. One is doing pushes, the other is doing pops. And we are looking at the number of messages over time, so we want this number to be high. So the number by itself means not a lot, so we can compare it to what you get if you do the easiest way to do a concurrent safe stack, which is taking the standard array stack and putting a mutex around it, right? So this is better, this is twice better, so that's nice, right? But if you look at what we have in Saturn, it's actually way better. And the stack is Saturn, is a Trevor stack. But even something that simple needs some work to be done to be actually efficient. And we have already done this work in Saturn. So hopefully at this point, you actually want to have a look at the repository. So what will you find in it? So in Saturn, we have multiple queues. We have the very classical Michael Scott queue, which is a multiple producer, multiple consumer queue, so normal queue. But we also have these queues that work only in a specific configuration, like the single producer queue, single producer, single consumer queue, that will only work if you have at most one domain pushing at any given time and one domain popping at any given time. If you have two domains pushing at one time, then it's not going to work the right way. It's going to give you some unexpected result. And the reason for this type of queue is that when you know about it, when you are writing the algorithm, and you have this type of restriction on what the domain can do, then you can basically take very large shortcuts. So this is essentially for performance. We also have work stealing the queue, which just talk, like the previous speaker just talked about it. So it's used in scheduler like the main slib. We also have a stack, an hash table that is actually not here but not in Saturn for now, but VESA did all the work. It's already in Picos, so it will be in Saturn very soon. We also have a skip list and a bag. And if you need anything else, please ask for it. Open an issue on Saturn and ask for it, because what we want is to provide you with what you need, and we need to know about it to do that, right? And so if you need a size function for a queue, for example, you can open an issue. Well, now we know that you need it, but yeah. I also wanted to ask that most of these data structures are log-free. I won't go into the definition of log freedom, but this is a progress property that is very nice to have. So we are trying to have all our data structure log-free, but this is not always possible. Like a blocking queue, for example, is not going to be log-free. And so we have two libraries. We have a library that is called Saturn log-free that contain only log-free data structure, and another one that is called Saturn that contain everything. So I told you that our data structure are well tested. And to do that, we have two main tools. We have Lean and STM that you can find in the multi-core test repository. And this library enables us to test for correctness and linearizability. Again, I won't go into the definition of linearizability, but Clément is going to talk about it. But it's basically in properties that when you have it, it makes it easier to get to reason about the behavior you have. The code have. So it's a nice property to have. We have that on all of our data structure, and we check for it with STM. STM is, by the way, a very nice tool that will generate for you random tests, so you don't even have to write tests with it, which is great, right? We also have DScheck. DScheck is a model checker, so for DScheck, you have to write the test. So for example, you could write the same type of test than the one that I showed you before, so you could have a test where you have two domains working in parallel. One is pushing, the other one is popping, both just once, and then when they are finished, you do one more pops. And at the end of that, if you are in the same implementation I showed you before, you expect the queue to be empty, so the size to be 0. And so you give that to DScheck. You state that you have a size of 0 at the end, and what DScheck is going to do as a model checker is going to check for all the interleaving in between the call to the atomic library made by the domain, the two domains that are working in parallel. And so the thing is, if you do this test in DScheck, the test that I showed you before, in 100% of the case, you are going to catch the bug. So this is great, right? And it's even going to give you the faulty interleaving, which is pretty good. By defect, by side, like a bonus that you get with DScheck is that if you test something that is not log-free, then it's never going to finish because it's going to generate an infinite number of interleavings. So if your test finish, you have kind of a good indication that your data structure is log-free, which is great because it's a very hard to prove property. Before I show you some benchmark, I wanted to talk about how we optimize our data structure. This work has been mostly done by VESA. So if you have questions about it, I will be happy to hear about it, but VESA will have the answer. So to improve our data structure, one of the main ways to do that is to reduce contention. You can obviously reduce contention by improving your algorithm, right? Like if you have a queue, for example, you may want the push and the pop operation to access two very different parts of your data structure, so you won't have contention in between this operation. But you can also reduce contention by preventing false sharing, which is now easier to do with the make contented functions that we have in the atomic module. There is obviously a lot of other ways to improve performance, like removing indirection, removing fences, like all this type of thing. And what we have tried to do in Saturn is to push our data structure as far as we could to see how one specific algorithm and one specific implementation in OCaml can go in terms of performance. And to do that, sometimes we were not able to not break the type checker, so not use magic. But this is still great to have some kind of limit of where we can go with an implementation. And furthermore, this has also been a way to test if one specific optimization actually is an optimization, is actually improving something. And this has been a way to, like a source of information for to add new language feature in OCaml. So you have right now an open PR made by Clément to add atomic record fields in OCaml. So yes, a benchmark. Finally. So this is a benchmark for queues. So you have 4 different queues. The green one is the unsafe one, the one using OpsMagic. The yellow one is the one that you, like the normal one in Saturn. I didn't precise, I forgot in the previous slide, but so we have this unsafe data structure in Saturn. They are called unsafe because this is this experimental data structures that are using Opsmagic. But you can find some of them in the repository, in the library. And so you have the yellow one. This is the normal queue. The red one is the standard library queue protected with a mutex. And the blue one is just the standard library queue without mutex, so it's just for one domain. And what you can see is, yes, very optimized with Opsmagic queue. The unsafe one is the best, but the normal one in Saturn is still pretty good, especially compared to what we could do, which is protected, which is use standard library queue protected with a mutex. So it's nice to have that. It's not really the case for one domain, and the reason for that is that writing a concurrent safe data structures that is also log-free, it's a lot of overhead. So we are working on improving that for one domain, but for now, this is what it is. And this benchmark has been launched on my computer, which is an Intel computer, and just as kind of a small overview as what you can, that's the mesh that you can get if you work on that. This is the same benchmark launched on Beza's computer, which is an Apple with ARM CPU. And yeah, the unsafe version is way, way better here. So yeah, there's quite a lot to think about and to tell, which I won't say today. So yeah, this is Clément's part now.
Hi everyone, can you hear me? Yes. I am Clément Alain. I'm a PhD student at INRIA Paris, and my role in this work has been to introduce formal verification in Saturn. Is that okay? Right. Thank you. So okay, so I'm Clément Alain, and yeah, I introduced formal verifications in Saturn, and well, testing concurrent algorithms is hard because you have to cover a wide space and with many possible alternatives. And so formal verification is also quite difficult, but it can be trusted. So what I've done is use the iris concurrent separation logic, which is fully mechanized in ROC, to specify and verify data structures from Saturn. So far, mainly concurrent stack, queues, and bags. So all this work is mechanized in ROC. So the first step is to translate the Saturn algorithms into ROC. So actually what we do is translate them into a deeply embedded language living inside ROC. So here you can see a simple push function from an assumed stack module implementing a concurrent stack. And at the bottom, you can see its translation. It's a deeply embedded translation. So I hope you will agree with me that it is pretty much the same code, except now binders are quoted, right? And actually, this transformation is manual as I'm being, but I am working on a tool to fully automate it. Right. So once we've done that, we have our algorithms in ROC. We can specify them. So as Karin mentioned, the standard correctness criterion for concurrent objects is linearizability. Roughly speaking, linearizability states that all concurrent operations should atomically take effect at some point during their execution, and we call this point the linearization point. And here you can see, well, in Iris, the way we do that, the way we prove this, is using what we call atomic specifications. So you can see the atomic specification of push. And what happens is, basically, it looks like a standard or triple with actually two preconditions and two pass conditions. So the two conditions inside curly brackets are standard as in all triple. So basically, they must be respected by the color of the operation. And the two other conditions, that's interesting, are they specify what happens at the linearization point. So basically, here you say that atomically during push, you transform the logical model of the stack from values vs to values vcons vs. Right? And crucially, this relies on the fact that we are working in a SC, in SC, so in a sequentially consistent memory model. Of course, you might be shocked by that, since you may know that the OCaml 5 memory model is relaxed. I haven't time to talk about it, but I have some slides in case you have questions. I just want to say that it is possible. There is prior work on that, and it's future work. Right. So to finish this brief overview, I would like to give an idea of what the proof actually looks like in work. So, well, I claim that the main points, like the essence of the verification of concurrent data structures like those of Saturn is to design a concurrent protocol. And what I call a concurrent protocol is basically a set of logical constraints that you want to enforce on your data structures, try to constrain its behavior. So here, to enforce the concurrent protocol of our stack, we write this stack inf protocol, stack inf predicate. So basically here it says that T, the instance T, is actually a memory location that always at any times points to a list of values that is actually the logical model of the stack, right? And I claim that given this predicate, you can verify this specification of push at the bottom. I will end it here. Thank you for your attention. I'll take questions.
To both of you. I'm sure we will also have questions here. We have time for a few of them.
So in some sense, the OCaml community is very new to doing all of this concurrent programming. And there's an enormous amount of work in other ecosystems trying to build best-of-breed concurrent data structures, both lock-free and not lock-free. And I wonder if you guys have done any looking at what are like the absolute best, you know, C++ and Rust and whatever kind of implementations for hash tables and queues and whatever of various kinds, and how the kind of implementations you're looking at here stack up against those.
I have just a few ideas on how to answer your question. Like, for example, the MySQL and the Traverse stack are used in most of the other libraries that are doing concurrent data structure in other language. So this is why we are using this implementation as well. For some of them, we actually, Visa did actually some comparison with, like for the single producer, single consumer queue, we did a comparison with an implementation in C. And it's not good. Like the OCaml version is not as good as the C implementation. So yeah, we are trying to find a way to improve that and to go where they are. But this does that answer your question, right? Does it?
I think it gets some of the way there.
Some of it, yes. Great.
Maybe a related question is, so when you are implementing such like a concurrent data structure and you take one off the shelf from, I don't know, a paper or a different language, and you find out that it's not as efficient as you would like to be in OCaml, what are the tools that you use to try to find out what is wrong and or what to look for? Like, are there any specificities of OCaml that you have to look for that make it hard to make those efficient, or yeah?
Yeah. Do you mean if it is inefficient or if it is not working?
Not inefficient.
Good question. Do you have a good answer to that, Veda?
Yeah. So the way you have to implement these things is that you have to know how the hardware works, because it's all about cache coherence, basically. So every time you read or write memory, it has an effect on the cache coherence protocol. And once you understand how those things work, you can sort of figure out how to make things that run fast. So that's the short answer.
But so if something works fast in C, doesn't mean that doing the same in OCaml will work fast, or does it? Or
as far as it's possible to do the same thing in OCaml,
Okay.
then it should work the same performance-wise. Of course, there's some minor details like integers in OCaml have the extra bits, so there's a little bit of overhead there, and there's one big performance difference comes from write barriers, garbage collection write barriers. So some algorithms are much slower in OCaml, especially those that use arrays. So that's one thing to watch out for. But basically, it's the hardware is what mostly determines the performance.
Okay, thanks.
All right, I have a question for you, Clément. I had no idea part of Saturn was verified. That's great to hear. How much of it is verified in this day?
So not everything so far. I would like to cover pretty much everything. But so right now, as I said, it's stacks, queues, and backs. There's also the work stealing queue that well, it's I need to finish the full mechanization, but it's on paper. And I am also working on the skip list, and then there is the hash table.
Yeah, what he's not saying is that obviously the skip list and the hash table is way harder to do. It's way more like line of code to prove, so it's a lot more work.
Actually, I don't agree.
Okay, we will talk about that.
No, it's more lines of code, but it's like less difficult than, say, the work stealing deck.
Interesting work. There was a bunch of work done in Haskell about implementing sort of dual versions of data structures and doing provability of that. I wonder if you've thought about, or whether it's possible to extract the code from Coq into OCaml and then compare it to the optimized OCaml version. Have you thought about doing that?
I'm sorry, can you repeat the question, please?
So you've got an optimized version of the data structures, and then you've proved that they're correct. Have you tried extracting the OCaml out of the Coq version and sort of using those as a comparison for correctness?
So okay, the question is, can we?
Can you extract? So you've proved things in Coq. Can you extract that OCaml code out of Coq? And is there any value in doing that and comparing it to your optimized version?
Okay, so the direction we have right now is OCaml, from OCaml to Coq. I also thought about the other direction. So that will be from rock to lambda, because basically reconstructing types is not a good idea. So what you could do, but I guess that would require a bit of engineering to basically plug lambda module inside a bunch of OCaml ones. So yes, that would be possible. Is that an answer to your question? Yeah.
Thank you.
Thanks for all three of you, actually. And this concludes our session. Thank you.
So welcome to the last session of the OCaml workshop. And I hope you're still awake. And so there's going to be an introduction on the new things on Opam 2.2 and the last year in Opam, I think, by Raja, David, and Kate.
Thanks, Pierre. So hello, everyone. As you saw, last July, Opam 2.2 was released. It was 3 years of work. Last major release, 2.1, was released on 2021. So it contains a lot of new features. There is some examples, a new command, Opam3, to permit to have to see the list of dependencies of a package in a tree view, and Opam-Y for reverse dependencies. The ability to do recursive pinnings, it is used in the case your package is not on top of your source code repository, and you can just specify a subpath also. There is also the software heritage binding. Software heritage is a project that aims to archive all open source software. And in Opam, we added a binding to their archives to be able to retrieve the source of a package when the main one is missing. And there is also the support of formulas. Formulas was introduced on 2.1 for switch invariants. And for 2.2, we extended that support to install commands, for example. And of course, there is, it's not the only features. There was a lot of enhancement about performance, UI, some quality of life improvements, and bug fixes, of course. So it took us 3 years. In the last one, there was 7 pre-releases. And after around 343 years later, Opam 2.2 was born. And speaking of quality of life features, usually it's option to already known commands like new way of pinnings or easy way to switch over your switches and things like that. Anyway, all that is for all the features are in the release note, the blog post. You can see, you can read that online. And you may notice I didn't speak about a tiny new feature in Opam 2.2, the Windows native support, but I'll let David talk about it.
So yes, Opam 2.2 has finally landed native Windows support. I think it's worth a little step back as ever to actually recap what we mean by native Windows support. The answer from our perspective is it's all about the C runtime library. So we heard earlier on today talking about WSL and WSL2 as ways of consuming OCaml on Windows, but this is a virtualization approach. It's basically giving you Linux on top of glibc. So there's nothing native about it whatsoever. It's a very good way of acquiring Linux OCaml on Windows, but it doesn't give you any ability to actually write Windows applications. There is also, from Red Hat, a solution called Cygwin, and there's a fork of that called MSys2, and that's slightly different. It gives a POSIX emulation based on the Windows API, but based on newlib, not as the C standard library. So it's almost native, but still not quite. These have been supported for quite a few years in OCaml and Opam readily. What we mean is GCC, provided by the MinGW W64 project, which gives you GCC on top of the C runtime library or the Microsoft UCRT, so the operating system's C standard library, or Microsoft C compiler from Visual Studio, which similarly is based on, unsurprisingly, on the Microsoft Universal C runtime. There have been out-of-the-box solutions before. I had a look on the INRIA website, and it turns out that there's been a binary zip of Windows binaries provided since OCaml at least OCaml 1.07, which is 1998. And I even discovered yesterday that that still runs on this laptop. So, INRIA provided a graphical installer until 4.2.3 that was maintained by Jonathan Prochenko that similarly installed the binaries of OCaml. Around OCaml 4.03 in 2016, OCaml for Windows was launched, which was a fork of Opam repository, but maintained by Andreas Hauptmann at FD Open, and he maintained that until around 2022. In August 2021, roughly, Jonah Beckford of Discov took that and added a lot more MSVC support to it and produced the DKML distribution, which until earlier this year was in fact the main recommended way to get native OCaml on Windows. So we haven't been we are not the first out-of-the-box solution for native Windows. We're part of a legacy of it. What is different, though, is that the OCaml installers that were provided before required the user to install and use additional tools. So if you wanted to use OCaml opt with the version from the INRIA website, you had to install Cygwin yourself, and you had to configure the paths correctly to be able to use it. Both OCaml for Windows and DKML bundled everything that they needed with them. They took an opinion on exactly how to get it and install it and recommend how to do that. They also end up wrapping Opam as a result, so you get this strange OCaml env exec utop instead of Opam exec or just utop. And similarly, DKML has a with DKML wrapper. And in all of these cases, the main Opam repository on GitHub was either not used at all, or it needed a lot of additional downstream work to be used. And so we can very clearly see that Windows OCaml was very, very different from Unix OCaml. And that's what we've tried to address in Opam 2.2. There were quite a lot of changes that we'd already made in Opam. 2.0 actually built and passed its test suite on Opam, and the compilers had quite a bit of support added for Windows that was inspired by the need for Windows Opam over the years. What was missing was the actual packaging of the compiler in Opam repository for Windows, a ton of shell support, and some other subtle features in the way package handling works for Opam file descriptions. I'll talk a little bit about that now. In order to build OCaml on Windows, you do actually need a Unix environment. I mean, OCaml begins with a configure script, so something's got to be able to execute that. And that officially is done using the Cygwin environment. So the instructions for OCaml had always involved beginning in a Cygwin bash prompt in order to build OCaml. But what we want to do with Opam 2.2 and what we've achieved is that we want Windows users coming to OCaml who have no background in Unix, not to need suddenly to learn how to use a Unix tool. So Opam 2.2 has the default ability to install a Cygwin installation automatically or not. So advanced users who wish not to do that can install and configure Cygwin and use Cygwin themselves and still use Windows Opam from it, or a new user who has no knowledge of Unix doesn't need to. As I said, the Windows philosophy is slightly different from the Unix philosophy in terms of querying things. So where Unix would have auxiliary programs to query things like terminal size, Windows has syscalls. It turned out to be an awful lot of glue that we had to put together on top of what's available in the Unix library. So we've now got well over 1,000 lines of non-trivial C stubs that we maintain, with none needed for Unix. Having this Unix support layer internally means that we've got two methods of paths going on. So Cygwin is a complete POSIX emulation. It has a root directory /, which Windows does not. So we can have paths coming from the Unix subsystem, paths coming from native Windows. We've got to be able to make the equivalent of Opam env work. We've got to be able to have packages that want to give descriptions of paths that are platform agnostic. That involved a very complicated set of rules that culminated in this xenv path rewrite that the very keen can go and see in the Opam manual. This allows us to specify portably updates to environment variables, which is a huge amount of work needed just to get Opam env to work and actually set path and all the other auxiliary variables correctly. Finally, having done that, we were then able to take the Opam repository compiler packages and upgrade them, which happened in mid-June, as I recall. And once all of that was put together, we finally have Opam 2.2, which actually works out of the box, with pretty much no special cases. And I shall give a short demonstration to prove this. So here you can see I have PowerShell. There is no bash prompt going to be visible in the course of this demonstration. We've been quite keen in this to make Windows Opam as easy to acquire as possible. We've been able to package it in Microsoft's Winget package manager, which is available on both Windows 10 and 11. So you can see here, it's the current version, so it's 2.2.1. It's actually downloading the exact executable from GitHub. It installs and configures it. I've already done that on this machine, at which point you then simply run Opam init, as you would on any other computer that you were sat at. At this stage, it gets slightly different. I'd mentioned that we know we need this Unix support infrastructure, and that gets put into place. What's happening here is that Opam is noticing that I perhaps know how to use Windows, and I have a few installations of my own. It's asking whether I'd like to use them or not, but still keeping the default option of saying, no, it would be safer if you just let me do this for you, so we can pick that. And then similarly, it moves on and does exactly the same thing for Git. It's got a little warning going on because it reckons that I've misconfigured this session, which it turns out I have. But again, it's giving an option to continue. So it's looking at what's on the system, determining if Opam can install that way, and giving as many options to the user as possible in terms of what they were actually expecting, rather than just mandating it must be configured this way or we won't work. That would take a little while to get through, so here is one I prepared earlier. Anyone who's used the Microsoft Visual Studio C compiler before will know it comes with a whole series of slightly arcane command prompts that you have to be able to get to. So by default, the C compiler CL is not available. That's one of the primary reasons for having these wrapper commands in the previous distributions. We've gone on a slightly different approach in Opam. So in fact, Opam manages that as part of an Opam repository package. So once I run the slightly strange equivalent of eval opam n for PowerShell, we now actually have the Microsoft C compiler immediately available, and you can see that I've also got OCaml opt for MSVC64. And that's all working quite nicely. I can then show that some of the tools are working. So if we have Jane Street's base here, I can start Visual Studio Code, which it turns out was on the wrong screen. And you can just about see that it's there with editor support. You can see there's an LSP server prompt coming up. And I think if I point at some of these, you can see the Merlin prompts are coming back. So we have tooling is working completely in the Microsoft Visual Studio port there. We've been able to take advantage of some of the things that Opam 2.1 added. So in particular, this switch that I've created here is based on the Microsoft C compiler. I can very quickly change that simply by installing a signal package that says switch to MinGW. Opam does a little bit of solving work that I now have to talk over while it does it. But there we are, we're ready. So, and you can see at this stage, it's saying, OK, we'll get rid of all of the MSVC support packages that we've had to add. We will then add all of the things required to switch to GCC on Windows, and then it will rebuild the entire switch. Again, that would take a little while. So here, again, is one I created earlier. And again, you can see that we now have both OCaml opt is there, and we've lost the C compiler. At that point, that didn't come in because it wasn't needed. And we can then show Merlin working in Vim for Windows, and you can see exactly the same effect here. If I do the type throwback down at the bottom, it's all working. The tooling is there. I am told there is another editor for Windows, but I don't know how to use it. What's still to do? Opam repository at the moment only has support for OCaml 4.13+. That should be fine because, of course, everybody's using OCaml 5. But in terms of parity, we will at some point later this year add 4.08 to 4.12 just to allow the same version matrix for libraries to be used on Windows as on Linux. The conf packages, which manage your external dependencies, some of those have been upgraded, a lot of them haven't. That's a blocker for just about anything using C bindings. It's very easy to do PRs for those, which I'll come to in a bit, but that needs to carry on being done. Opam 2.2, as we've already said, took a little while, and as a result of that, originally OCaml 5 was going to be tied to there being Opam 2.2, and we kind of missed that boat. So there are various temporary workarounds and solutions that have been necessary for acquiring that on Windows. And now, of course, it's confusing because there are lots of sets of instructions, so we need to go through and find all of these workarounds and get rid of them. And Opam repository at the moment, while it's testing new PRs for Windows compatibility, it's not yet able to do bulk testing, and we hope to sort that out later on this year. The key thing about this is none of that actually requires a new release of Opam. That's all stuff that will just be one Opam update away once it's done. In terms of Opam, that little crazy expression that you had to type in PowerShell in order to get OPAM-env to work is not something that one's expected to have from memory. There are other shell integration things still in the pipeline to come. And unfortunately, the first time you run Opam update, you'll discover the need to make coffee. And we will be looking at performance improvements for some of these aspects under the hood. So it works. It doesn't always work quickly. Can you help? Yes, you most certainly can. You can help out updating conf packages on Opam repository. There are sample PRs for doing it. There have been Discuss posts about it. There are blog posts. There are Discord ways of reaching out to people. That's exceedingly helpful. There's no competition for who gets there first. More importantly, you can test your libraries and your packages on MinGW64 and or MSVC. And having discovered that they work, you can go, woohoo! And if you do not discover they work, please report bugs on any issue tracker that you can find from amongst this list. I don't mind where it goes as long as we end up hearing about it. And with that, I shall hand over to Kate.
So, speaking of issues, This is a screenshot from OCaml'22, so the OCaml workshop in about 2 years ago. And David said, like, Opam 2.2 will be released in a few more months, hopefully. Well, didn't really happen, so Opam 2.2 was released a couple of months ago instead. So what happens? Well, you can imagine Windows is hard. David is pretty knowledgeable about Windows, but some of us are not, so we had to learn a lot of things that are Windows specific. So C API, PowerShell, many things. Anyway, so those things are really hard. So it means that everything that you've done in the meantime, other bug fixes, features, and so on, are blocked by Windows. So everything gets queued, and it gets frustrating. It's a frustrating situation for users and us as well. The reason is historically we have tied releases with features. So for example, 2.2 was a release that was going to be Windows. 2.1 was Depext and Opam lock. 2.2 is a bit special, but you get the idea. And to add onto that, you also have founding that are tied to features, and features are tied to releases, so everything is like a circle. So how do we fix this? We've decided to switch to a new release cycle, to a new release schedule, and there's going to be a time-based schedule. So every 6 months, we're going to do a release, similar to what the compiler or other big open source projects do. We'd like to do around October, April kind of thing to avoid big vacation and so on, but this is the idea. And we're fairly confident in 2.2 we've added a lot of tests, and we're fairly confident that new PRs won't break things, hopefully. Which means we can just at some point say, yes, we branch to a new branch, and then we do a release cycle. This way, we also avoid issues with the annoyance of waiting for a release for external contributors and users. And to prove that, we are currently doing the 2.3 release, which is slightly early than usual, just because we have things that we've done already during the 2.2 cycle, but we didn't want to merge it right away to avoid delaying again, delaying the 2.2 release further. So we've had a lot of things to merge. And so the next release will be there in next month, probably. Speaking of release, how releases are done, just to explain a little bit for those who are not aware. So Opam has 3 active maintainers, so 3 of us, me, Raja, and David, as well as some maintenance and training and external contributors. For example, a few highly valued contributors have contributed things like Opam tree and the WizDev setup new options in 2.2. And just to explain like the job of a maintainer, we do community things like speaking here. We fix bugs. That's usually what people think when talking about maintenance. But we also think about how to make Opam evolve so things don't get stale and the OCaml ecosystem can grow and go forward. Speaking of going forward, I'm going to pass it on.
So, what's going next? As Kate said, there will be the 2.3 release. So the Opam 2 series will continue, but of course we have in mind Opam 3. But before that, we want to achieve some steps, some user surveys. Want to retrieve some information about how Opam is used today. What are the main workflows? What are the most used commands? For example, the unknown ones also. And we also want to discuss with the community about Opam future, what they want to have in Opam 3, what are the main missing points, the things that they want to change. It's very open discussion. We will do that as special public meetings on top of our weekly meetings, the weekly meetings. And we have already some ideas for Opam 3, some change on the package file format, but in a more smooth way than Opam 2. We will try to maximize the backward compatibility to avoid breaking things. We also want to rework and rethink some process like package installation to take advantage of relocation and caching. And also, for example, rework also the external dependency mechanism to have another way to specify and probe the information from the system. These are just small ideas of a long list, and it's open to discussion anyway. And for the surveys, for for Opam Future, we will publish everything on OCaml Discuss. So keep an eye on it, and we are here to talk. So reach us. Thank you.
So there is a question from the Discuss, which asks if there is an external library on Windows, how you're supposed to install it. Like the example was GMP, for instance.
So yes, there is. A lot of those are actually getting via Cygwin. So they are used internally added. So the depex mechanism manipulates the internal Cygwin package. There are quite a few examples of that already in Opam repository. In fact, I think GMP may already be done. So Opam install conf GMP, which should almost certainly work. But yeah, we can continue that as a pointer offline.
If I install Opam on Windows like today, and I use it to build my OCaml software, I didn't quite get what the binaries that I obtain in the end depend on. Can I give them to my friends? What can I do?
Yeah, so if you compile them with GCC, with MinGW, that executable will just pretty much run straight on any Windows machine you send it to, possibly Modular or runtime DLL. If you compile them with MSVC, you just have to install occasionally install the latest version of the Microsoft C runtime. But yeah, they're basically copyable.
Thanks.
Just like OCaml 107.
So, other question? Let's thank the speakers again. And so, I'll present you Tim Williams from Bloomberg, which will be speaking about some way to write some kind of generic recursion patterns with examples in compilers.
Hello all. My name's Tim Williams from Bloomberg, and there's quite a few of us Bloombergers here this week, so hopefully you've had a chance to meet at least one of us. Today I'm going to talk about one of the many OCaml projects we have at Bloomberg. Although not really much about this project, it's more on an implementation detail really, but the project I work on is essentially a domain-specific language to model bilateral financial contracts. So these are typically derivatives contracts with two counterparties. The language we have is a restricted pure functional language with no recursion. It has a set of primitives and a means of composition, so we build larger contracts from smaller ones. And we target a contractual representation, essentially a tree, not that dissimilar to the one discussed in the famous Composing Contracts paper from 2000. But crucially, we have users, which is not guaranteed when these projects get kicked off. But we do now have many users. We've been going for 10 years. And our users are typically financial engineers. So these are sort of experts within Bloomberg that take term sheets and turn them into, use this DSL to turn them into a representation that the computer can understand. So this talk is about an experience report based on our use of recursion schemes. And the goal for building our compiler using recursion schemes was really to achieve the following: to factor out and share traversal code, to make use of pattern matching, because we like pattern matching, to better communicate and reason about our traversals. This can be hard when it's explicit recursion everywhere. And of course, to easily identify and exploit opportunities for optimization, and I'll talk a bit about that. And of course, use a catalog of theorems to guide us in the above. So use all the knowledge that has been published over the years about this stuff. So let's start with a sample expression type, not that dissimilar to what we have in our code base. This expression has integer constants, free variables, an add operation, and potentially more. This data type is inductively defined, so it has the syntactic fixed point baked in. So the add operator here refers to expression. And this fundamentally limits what we can do with this type. And there's quite a few papers. I think data types a la carte is one that I recall that talk about all the possibilities if this recursion is opened. We can work with this data type, of course, and traditionally fold functions are often created to sort of factor out the traversals. But these typically work by, these are typically higher order functions with a function per constructor. And so parsing and composing many functions around quickly becomes somewhat awkward when you scale up to complex data types with many constructors. So let's define a non-recursive data type. Let's factor out the recursion. Let's make it open. And so that's what we're trying to do here. We'll call it expr node. So now the add operation refers to the parameter r. We tied a recursive not at the type level by defining the expr type. And then we need these term level functions on the right to inject into this type and project out of it. So why are we doing this? Let's remind ourselves of a bit of category theory. So what we want to do is think in terms of F-algebras instead of thinking in terms of folds. An F-algebra is essentially a triple. The end effector, or the F, is expronode. It's a, the category here is the category of OCaml types. And then we need a carrier type B, and then we have a morphism of B expronode to B. So this is these are the functions that we want to think in terms of. And in fact, the triple expronode, expert, and fix on the previous slide, defined on the previous slide, is itself an F algebra, a special one, the initial algebra. So essentially, we are building folds, but another name for a fold, or the category, the name in category theory is a catamorphism. It's a generalization of a fold. For a list, obviously, it's bracketing from the right. For a tree, it's a bottom-up traversal. And in our code base, all our traversals are fundamentally one or more structured forms of catamorphism. And we actually use F-algebra combinators to add more structure. So we're thinking in terms of F-algebras. And so many of these combinations have fancy names, paramorphisms, zygomorphisms, and so on. But they're all, essentially, they are combinations of adding structure to a catamorphism. For top-down traversals, we achieve that by folding to by using a function carrier type, a higher-order carrier type. So let's derive the catamorphism. So we can do that quite nicely with a commuting diagram from category theory. The initial algebra is on the left, although I've flipped the arrow. I flipped the arrow because the homomorphism at the bottom, cataralg, the function, this function I want to derive, and I can derive it by saying, well, to go up the diagram, we'll compose unfix with map cataralg, and then we'll go down the other side with alg. So, you can that definition in OCaml is read straight from that diagram. I've used function composition to define it with this operator, and this obviously relies on a structure preserving map, which works as one would expect. So let's have an example. This example is substituting variables. It's a fold, but it's defined in terms of an algebra, and it takes an environment, and when it encounters a variable, it will look in the environment and it'll replace it if it finds it. And then for all other cases, we delegate to fix. And actually, it's often useful to delegate like this. And here's another example that does so, collecting free variables. With this example now, if we find a free variable, we create a singleton set for a set of identifiers. And then all other cases, we delegate to another F-algebra, this one parameterized by a monoid with union and empty. And now, in our code base, we write things a bit differently. We actually make the algebras the top-level functions themselves, and because normally those are the things that we're thinking in terms of and composing. But here, to sort of more easily relate it, the algebras are defined as internal definitions. So here's an example of an optimization that we did. The hash consing, some of the contracts that our DSL generate have quite a large in-memory representation because it's a mostly first-order representation. And the F-algebras actually give us a nice framework for implementing hash consing. We need to provide only an alternative recursive type and an injection function to do this. The hash table we used by repurposing OCaml's weak hash set. It's only a few lines of code away from being a weak hash map. And we followed that tip from this paper here. So how do we do that? Well, we create this hash-const wrapper type here that lets us store a pre-computed hash and a unique tag, which is sometimes useful. And we build a new expra. This time, instead of just being expra node, we're now stacked on hash-const there as well. And this is the sort of thing that the open recursive types allow you to do. And obviously, there's a little bit of boilerplate. We need to define equality and hashing for our type as well. That's all pretty straightforward. And then we have an OCaml functor here to make to support hash consing. So there's obviously a create to create a table, and there's a hash cons that will take the table, take a term, and then it will check if the term is in the table. If it is already, it will return that instance and discard the one it's been given. If it's not in the table, then obviously we'll add it and return the instance it was given. So how might this work? Well, here we create a hash cons table at the top level, and then we change the definition of fix and unfix to accommodate the hash consing. So that's the only change that needs to be made, you know, this optimization is therefore pretty non-invasive. It's pretty a small change. Memoization, this often goes hand in hand with hash consing. So we're trading space for time here in certain where necessary. And since we restrict recursion to a library of standard combinators, we can therefore define memorizing variants that can be easily swapped in. So here's a memoizing catamorphism. It's built on another function, memorec, which you would implement very easily with a hash table. So what are the experiences? So the good is that recursion schemes have helped us structure our traversals and reduce boilerplate. We've been thinking in terms of F-algebras and F-algebra combinators, and this has helped us to compose and combine traversal code. When you're thinking in folds, it can be, it can be hard to fuse the loops, so to speak. The end-effector representation, or the open recursion representation of our expert data type, has allowed for specific variants to easily be created, the hash consing variant, but also for serialization, for example, transforming the tree to a graph. It's helped with that as well. And our developers have welcomed these abstractions, which are more principled than most other boilerplate reduction frameworks. And the runtime performance has been more than satisfactory, so that's really credit to the OCaml compiler there. Some not so good experiences. So our recursion scheme operators like kata memo are not data type generic. So if we had a different expression type, we'd have to define them again. It's not been a huge problem for us, but obviously we could try to use OCaml module functors here to implement each operator only once. Probably a bigger problem is that the memoizing operator, kata memo, does not work in general when you have a higher order carrier type. So it obviously only caches the creation of the closure, and when you run the closure itself, that works top down, that won't be cached. So we had to work around that by creating sort of specific concrete variations of kata memo for particular problems. So that's annoying. But I suspect that some clever OCaml functor stuff might help with that, but we haven't explored that. And yeah, there's a lot more that I could have talked about, but that's the gist. So thank you for listening.
So we have plenty of time for questions. So have you considered generating the base kata memo and other things like that from PPX? Or
It's something that that we'd be interested in exploring. The answer is no, but it sounds like a good idea.
Just out of curiosity, do you ever solve the expression problem? Do you ever have the combination of different languages that you put together?
Well, is this a question about
application at Bloomberg? If you ever want to extend an existing DSL with more operations and at the same time with more constructs in a modular way?
I understand, yes. No, it's not something that we've tried to solve. We're quite lucky in that there's only the internals of our compiler is not something that we need to publish, and we're sort of free to change that. The problems with compatibility that we have are really around the language itself, which is a different beast. Yeah.
Okay.
Thanks.
Hi. It's a bit out of curiosity as well. Did you try to interact it with co-inductive data types? Because for recursion schemes, sometimes we can have things to manipulate with co-algebras like streams, like sequences. I don't know if that could help, because it looks like it's at a nice level of generalities. So I don't know.
No, that's not something we've explored.
Okay. Thank you.
Thanks.
Let's thank Tim again. And now is a remote talk, so we'll see if it works. So, hello, Rokas Urbonas. Thank you. And so Rokas is going to be presenting a DSL for choreographic programming in OCaml. So you can start now, whenever you want. So there are apparently some network problems. So I see a few pixels moving. this would work far better if it was written in OCaml.
Hello.
And
Wonderful. Should I?
perfect. You can go on.
Okay, cool. So, hello everyone. I'm Rokas from the University of Cambridge, and I will be presenting about CoreCaml. So, oh, sorry. Let's just restart the presentation. Sorry, I'm having some issues. Just give me a second. Okay, it should be fine now. So I will be presenting about CoreCaml. So it is the first embedded domain-specific language written in OCaml for choreographic programming. The goal of it is making distributed programming easier for the programmer and less error-prone. Here at the bottom, you see a quick sneak peek at the bookseller protocol implemented using CoreCaml. I will explain it in detail a bit later. So first of all, what is choreographic programming? It is a paradigm for writing distributed programs. And unlike in naive approaches, instead of writing a separate program for each participant, the programmer writes one big unified program known as the choreography. One of the restrictions of choreographic programming is that all participants need to be known at compilation time. And furthermore, choreographies are defined over an arbitrary communication backend that uses message passing. Sorry, just a second. I messed up my presentation again. Okay, sorry, should be fine now. So, and it is often convenient to define choreographic languages as an extension of some base language, which provides local expressions, and the choreographic part simply augments the type system with locations to represent participants and provides safe communication operations. This in mind, let's have a closer look at how this might look like in practice. And for this purpose, I will present the bookseller protocol. In this protocol, we have two participants, a buyer and a seller. The buyer wants to buy a book from the seller if it is within their budget, and if that is the case, they want to get a delivery date back from them. A naive approach of writing this would be implementing two separate programs which communicate between each other using send and receive primitives. On the left-hand side, you see the buyer program, and on the right, the seller program is present. So using this approach, the programmer has all the responsibility for correctly matching up the send and receive operations. In case of a mismatch, severe errors occur which become visible over time and are usually unrecoverable. And this is largely not ideal, and that is what choreographic programming attempts to solve. So this is a pseudocode example of what a choreographic program for the bookseller protocol could look like. As you see, the main difference is that the two programs are now joined just into one piece of code. We make use of the which in this case, that being the variable t at location buyer. Lastly, we have choreography level branching. It is interesting because it performs some implicit synchronization between the participants. The conditional is located solely within the buyer, who makes the decision whether the price was within their budget. And based on that, the respective participants of the choreography are informed of it automatically, so they can proceed as expected. In this case, if the decision to buy the book was made, the seller would send back the delivery date, and otherwise, the program just terminates returning none. Now, to execute this program, you would need to make use of the compilation technique known as endpoint projection. At its core, this is a technique that takes the original program, a location for which to compile, and then it produces executable code just for that location. In the previous example, we would call endpoint projection once with the buyer program and once with the seller program to end up with two separate executable programs. And those programs could be executed in parallel, and they would communicate correctly. With this approach, the programmer does not have to manually write the send and receive operations and try to match them correctly, but they can simply trust the compiler to do the right thing under the surface. Now, with this background, where does CoreCaml stand? First of all, it is an interpreted language. It is embedded as a domain-specific language within OCaml. Provides a functional interface using the FreeR monad and offers high levels of modularity. This allows the use of a variety of communication backends and interpreters for the programs written in CoreCaml. And the main one being the TCP backend included with the implementation. I should mention that this project was largely inspired by Haskell, which, as you might have guessed, is a Haskell library for choreographic programming. Now, let's take a closer look at the implementation of CoreCaml. The first point is the representation of values. The representation of locations. This concept needs to be unique on the type level to ensure safety. But since we're using an interpreted approach, we also need to distinguish between locations at runtime. So they need to be unique on the value level as well. For which reason I chose the representation shown in the lock_s module. Takes a type and a UID integer used during runtime. Then for convenience, we wrap it in a type alpha lockmod, where alpha is the type unique to that specific location. And lastly, we have an example of creating an instance of this location module. This is slightly clunky, but it can easily be extracted into a PPX to perform most of these actions. So first, we would define a new type, AliceLock. Then we would create an appropriate module of the lock_s signature by passing AliceLock as the appropriate type and providing some unique ID. And lastly, we wrap this module into a value for convenient use later. Now, with the location representation sorted out, we can take a look at program value representation. So program values are effectively arbitrary OCaml values paired with a location module. This is represented in the lockval data type. It is now, the one unusual thing to note here is that an empty clause is also provided. This is, once again, because we have taken an interpreted approach. And occasionally, our interpreter will be processing expressions which are not intended for the location that is currently being interpreted. In that case, we need to skip the expression, and we simply return an empty value to indicate that this was skipped. Now, it might be slightly alarming that the unwrapped value would fail in the empty case. However, the rest of the language definition and all the data types involved in it are structured correctly in a way that ensures that the type system would catch cases where we're trying to unwrap an empty value. This similar approach was also taken in Haskell. Next, we can move on to the choreographic primitives. And, sorry, the primitive expressions of choreographies. And this is highlighted in the following data type. The three main cases to note are, first of all, var. This case of the GADT takes a location module, an arbitrary OCaml value, and uses that to create a located value. Next, we have app, which takes a located function, a located value, and uses them to create an appropriate value of the same location, which is the result of function application. And lastly, we have the com primitive, which takes a location module and a located value. And the result of it is the same value located at the destination module. This is the expression that gets converted to send and receive primitives by the interpreter. Additionally, I have omitted this here, but we have a branching primitive as well. It serves just for convenience and can be implemented using the other primitives already. Next, to facilitate the implementation, I made use of the FREER monad data structure. In essence, this is a highly versatile type that simply represents arbitrary type-aligned chained expressions. And it is defined abstractly over a box module, which in our case will be the base choreo type I provided before. And the FREER consists of two cases of this variant type. Pure just signifies the end of expression sequence, and impure can be seen as the head of, sorry, and impure contains the head expression followed by a continuation that returns the remainder FREER monad. This is once again highlighted in the bind operator implementation for the FREER monad. And later in the presentation, I'll be using the binding operator syntax instead of the bind operator itself. And as I mentioned, we use our base choreo type to instantiate the FREER monad, and that creates the choreo module, which provides all the main utility functions for writing choreographies. Now, just before I jump into some usage examples, I also implemented a couple of convenience operators. So the user doesn't have to work directly by using the variant constructors. So the first operator to note here corresponds to var. It just takes an arbitrary OCaml value x and the location module loc to create a located value. Next, we have two operators for communication. They do effectively the same job, except one of them first lifts the given value to the choreo monad, and the other one just passes the values to the communication primitive immediately. And lastly, we have two more operators which correspond to the app primitive. Once again, one of them performs a lift before doing the rest of the logic. And I should note one thing. Some of you might have noticed that lockval roughly forms an applicative. This is sort of highlighted in these two operators, which more or less correspond to the main two applicative operators. However, the type signature doesn't match perfectly because we're wrapping the result into a choreo monad, and therefore I chose slightly different characters to represent these two operators. Now, we can come back to the bookseller protocol implementation in CoreCaml. This is the same protocol as highlighted before, and what's happening here is that we're sending the title value over to the seller, which produces the located value t, which is located at the seller. Next, we're using the caret operator to call getPrice on the title at the cellular location. And then we're using the arrow operator to send it over to the buyer, which together results in the value P located at the buyer, containing the price of the book. And next, the buyer performs the decision locally. This happens once again by using the caret operator. And here we just have a curried version of the comparison operator that's pre-applied with a budget constant and then compared to the price P. This results in a Boolean decision located at the buyer. And next, we're using the branch function, which is somewhat self-explanatory based on the Boolean value located at the buyer. It performs either the first branch, the true branch, or the false branch. The latter case just returns a non-value at the buyer, while the former case performs some more logic to get the delivery date out of the seller to the buyer, and then simply wraps it in an optional value. Now, once we have a choreography like this, the library provides two main ways to execute it. The first one is local execution, and it is trivial in that it simply runs the program in a non-distributed fashion in a sequential way, and that is simply useful for debugging purposes. And then we have the second interpreter, using the aforementioned TCP backend. In this case, we pass the bookseller choreography, a certain TCP config, and the location for which we're executing the program. And this uses LWT internally for asynchrony. So we pass it to LWT main run to actually execute it. And for the bookseller protocol, if we had two instances of this running, one with buyer and one with seller, we would have a successful communication between them, producing either a delivery date at the buyer or just nothing if the buyer decided not to buy the book. Yeah, that more or less sums it up. I have also included a slightly more extensive example of a choreography using OCaml. Here we have the three-phase commit protocol, where Alice and Bob participants communicate between each other with the help of a coordinator, and based on their results, they either commit their votes or don't. Yeah, I have also included an example of the same three-phase commit protocol in Haskell. It is a bit more verbose, and one of the things that OCaml tried to improve was the verbosity of the unwrap operations, very, very frequently present in Haskell. Yeah, thank you for your attention, and I'm happy to take any questions now.
I have a question on upgrading Haskell programs. So obviously you have this maybe running on different systems. Does the upgrade need to be atomic with all participating programs at once, or is there some kind of support for versioning possible in the communication protocol?
Mm-hmm. Yeah, unfortunately, there is no support for convenient upgrades. The programs should be compiled from the same exact source code at the same time.
Thank you.
So thank the speaker again.
Yep. Thank you.
So now our last speaker is Romain Calasibeta, which is going to present us some horrible hacks, I think.
So hi everyone, so I'm Romain Calasibeta, and I will show you software that we developed 1 year ago. So Bob, an universal peer-to-peer file transfer in OCaml. So the program is available on the website, and let's start with a demo. So you just need to download the Bob binary, and after you just need to drag and drop the file you want to send, and Bob gives you a little password. And the receiver just need to double-click on the Bob binary. He just need to put the password, and he receives the file. So it's really straightforward, just to share some file between two persons. What is really interesting is actually Bob works on Windows, Mac, and Linux, and it's exactly the same binary. We don't try to build for Windows, for Mac, or for Linux. So I know that someone will be happy about that. How to do that? You need to make a Windows executable. And so as you can see, you see the magic number of Windows. So bob.com run natively on Windows. And for Linux, Mac, and BSD, this system considers bob.com as a shell script. And from this shell script, we can start to launch some command and recognize the host system, and particularly the architecture, if it's a FreeBSD, NetBSD, etc., etc. And if it's Linux, for instance, we just emit the magic code for the Linux program, so the ELF. And for Mac, we just need to make a new file, put the magic code for Mac, and execute this new file, which is in the temporary directory. So at this stage, we are able to run any assembly code in any platform, and we use the advantage of fat binary to run x86-64 and IRM64 program. So we just need to compile twice the program and just concatenate the assembly code. And after, it's just about jumping on the right assembly code. But we now have another issue. It's like we need to interact with the system. So we need to think about how to interact with any system that we want. So for the Windows case, because we run natively, we just need to load what is needed to communicate with the Windows kernel. And we would like to provide like a sys5 API, something close to the sys5 API from Windows. So sys5 is really old, but on the other side, the sys5 API is already provided by the other system. But the value expected to communicate with the kernel is different for each system. So for instance, you have few value, and each value corresponds to each system. And what we do, it's like at the boot of the program, we will inject the value depending on the system. So if it's a BSD, we will inject the value for BSD and so on. And on top of that, we can start to make ellipses. So we start to reach the sky and make an actually portable executable with C. But we are in the OCaml workshop, so the question now, it's about OCaml. And for OCaml, it's pretty straightforward. It's like we just take the compiler and we just try to explain to the compiler that the link step is different than what is usual. So instead to use LD, we will use the actually portable executable linker. And we would like to compile the libasm run.a, so the OCaml runtime, with our libc. And of course, at the end, we would like to statically link everything. And so we just need to provide another toolchain. So it's not pretty new to do that. We already did that for 10 years ago with unikernel because it's the same things. I mean, we want to make operating system, we want to statically link everything, and we want to link with another libc that the host libc, so the no libc, for instance, for unikernel. And at this stage, we are able to produce a actually portable executable, and you can check that on the Esperanto project. So Bob is not only portable, it's about how to share a file between two persons. So the question is how to check that two persons have the same password. So we will use the SPAC2 plus EE protocol. We have like 30 protocols for this, but this one is good. I will just explain a little bit the protocol. So Alice and Bob have the same password. Alice will try to generate a salt and generate 4 values, M, N, K, and L, send the salt to Bob, and Bob will generate elliptic curve point from the M value, so the name is X. Bob will send X, and Alice will do the same, but with the N value, and she will send also the Y to Bob. And both of them will try to infer the Gx for Alice and the Gy for Bob from the X and the Y they received. And from all of that, we will try to generate a bunch of values, so especially Z and V, and we just need to concatenate this value and split out the result to 4 parts. And what is interesting is we need to send now the VA on one side and the VB on the other side. And all of them need just to check that the VB received is actually the same VB that I calculated. And if it's done, we can say that the end check is done. So if we come back to OCaml, we can express all of these packets via this ADT. So as you can see, you have the salt, the X, and the Y, and validator to check the agreement. But it's not only like one Alice want to send a document to Bob, it's like multiple Alices want to send multiple documents to multiple Bob. So it's like you need to have a place, a rendezvous place. So we talk about a relay. So we need to extend a bit the protocol to be able to recognize each people in this rendezvous place. As you can see, I put in comment some constraints. It's a comment, but we can say that, for instance, the hello as Alice is a packet which comes from Alice, and the destination of this packet is for the relay. And we actually can gedit that. We just need to put some type and put some constraints, so that's free. But what is really interesting is, like, if I take the protocol, Alice will never talk to another Alice, and Bob will never talk to another Bob. Alice will talk to Bob and will talk to the relay, but we have a kind of duality between Alice and Bob. So what we can do is, like, we encode this duality in GADT, and by this way we can say that Bob should receive only packets that the destination is for Bob, and it's the same for Alice. And as you can see, OCaml is able to check the exhaustivity of the pattern matching. Instead to have 9 cases for the protocol, we have only 4 cases for Bob and 3 cases for Alice. The relay is a bit much more complex because it's like you want to receive some packets, so the special hello packet from Bob and Alice, and the last case it's only transmitting a packet through the relay. So when Alice wants to talk to Bob, she wants to talk to Bob through the relay. So it's like we just need to put this case of transmitting packets, so we don't care about the packet. And actually, if we really care, the X value is factually the opposite, so the non-X. So if X is Alice, non-X is Bob. And the GADT can say that. So we talk about incoming packets, how to process them. So let's start to talk about how to send packet. So we just need to extend the constraints and say that, okay, we just, Bob should send only packets that the source is Bob, the same for Alice, and the relay has the same with the transmission case again. So at this step, we have the protocol implementation, and now it's about the relay. So that's the last role on the transmission. And the relay is obviously a unikernel. So it's only 3 megabytes. And so we don't have a file system, we don't have shell, we don't have SSH, we have nothing. We have just a TCP IP stack, and we just talk in the Bob protocol. So by this way, we delete all the side channel attack possible for any system, because we cannot do nothing else than talk with the Bob protocol to the relay. So you can you can launch the unikernel via this command with Solo5. So Solo5 is a tender. It's like the bridge between the unikernel and the host system. So when the relay wants to send or receive a TCP IP packet, it will ask to Solo5, and Solo5 will ask to the host system. Of course, we have developed a tool for that. The name is Albatros, if you want to deploy many unikernel as you want. You can also deploy the relay on the Google Cloud platform if you want. And you can do that on the smallest instance of Google Cloud. And even the smallest instance is really big for such a unikernel. And of course, I deployed the relay on my side, on my server, ozo.ri. So Bob is also a compression algorithm. So for instance, if you want to send 15 gigabytes of documentation, we will try to compress that to 250 megabytes. So the ratio is big. So 50 gigabytes, 200 megabytes. So it's a compression à la Git. We do exactly the same. We use an internal DNS resolver, and by default, we use the uncensoreddns.org, which is against the censorship. Also, the bob.com, the binary, and the relay are reproducible. That mostly means that if you want to build by yourself this program, you will get exactly the same result as us, byte per byte. So it's available on build.ozo.ri. And you don't have transfer limit, so if you want to share the last season of The Ring of the Power, you can, for example. And for the next things, we would like to be able to send the file in the anonymous way via the Tor network. So the pull request is available, but it changed a bit the protocol, and we would like to finish another feature. It's like resume a failed transmission. So if you failed, you can resume and just do what is missing for the transmission. We would like to also take the advantage of capabilities and sandbox from the host system. So seccomp for Linux and pledge for OpenBSD. It's mostly to say that, okay, Bob will not try to do something weird on your system and will just make some bunch of file. And for the local network, we would like to implement the norm protocol. So it's like a TCP over UDP protocol to share so document over the local network. So I would like to thank to Justine Tenay, who made the Cosmopolitan and the actually portable executable. It was really pleasant to work with her, and she is aware about the OCaml and the Esperanto project, and we tried to fix together some bug. Arma Elgeno, because we did the idea of how to transmit a file together the last years. He asked me to share a unikernel, and we did not get, we are not able to share a unikernel, but now it should be done. And the Robur Cooperative, of course, because they let me to work on that for 3-4 months, and they also participate. And so if you like what the cooperative does, you can donate and give us some tips. And of course, thank you for listening to me. And if you have any question.
Hey, so I've implemented most of the BitTorrent protocol on OCaml, and there's like some things in that spec that just kind of suck. So I'm wondering whether you've thought at all about extending something like this to be distributed, distributed like BitTorrent. So
actually, it's not really distributed. It's like peer-to-peer. After we have a question about conflict between like two people as probably we have a probability that two people have the same password than some other. So of course the password is generated randomly. As you can see, we generate here the password. And after it's just like, okay, we check that they share the same password, so we can generate some cryptographic key and just send the file directly to the destination. So it's really peer-to-peer.
But you're not interested in extending it to be something distributed?
So actually, that's a kind of idea for the UDP protocol. I would like to take the advantage of the copy of packet on the UDP level to share to someone else. But yeah, we need to implement the UDP layer.
Is there any hope to have the same executable for different architecture, like x86 and ARM?
Yes. Actually, it's like we just, as I said, we just need to compile for ARM64 and x86-64, and we just concatene all of that. So the binary is like about 16 megabytes, but so it's a bit huge. But yeah, after it's actually portable, executable.
How does that work when the two Alice and Bobs are both behind a NAT or something like that? Does that go through NAT?
Does that go?
Can you do some hole punching, or how do you actually do the peer-to-peer connection?
It's like just a transmission through the relay.
Okay.
Yeah. It's like when the agreement is done between peers, the relay allocate a secure room. But again, the relay does not really care about what is going on and does not have any information about the key on both sides. So after, we just need to encrypt on one side, encrypt on the other side, and for the relay, it's just like a bunch of bytes that you need to transmit from one side to another. But again, the UDP, the big thing about the UDP is to delete the relay and be sure that we can share without the relay.
Thanks, Romain, again, and Armel has a few words for us.
Yeah, I think we even have a little bit of time, of official time left. I mean, that's it for today and for this year. Thanks for coming. One last thing from Sonia and I. So next year's ICFP, as you probably know, will be in Singapore, and the OCaml workshop will be co-located with ICFP as usual. So that should be very nice. At the same time, we were thinking with Sonia about that some of us are based in, for example, Europe and might not want to fly there for maybe environmental reasons, but would like to participate on the fun. So we thought that maybe it could be the occasion to experiment with something that I know some other academic events have been trying, which would be to maybe try to have something like a parallel event running somewhere in Europe at the same time with, for instance, talks being streamed live there, and so where some people could gather and do some OCaml stuff. I think some people could call that a hub, and you'd have a local hub for the conference. This is very much up in the air at this point. It's just me and Sonia thinking about it. But yeah, if you have any opinions, ideas, or would like to help with that, we're happy to talk. And yeah, that's it. That's it for me. Thanks, and see you next year, perhaps.